Have you ever felt that the universe holds a secret pulse you can almost hear? Imagine that the void you see around you is actually alive with invisible waves of energy. In the next few minutes, you will discover how those hidden fields shape everything you are and everything you can become. Let us awaken your curiosity and invite you to see reality as a living, breathing dance of possibilities. The story begins with a simple but profound observation. Empty space is not empty at all. It is filled with quantum fields that ripple and vibrate in every corner of the cosmos. Those fields are the stage upon which particles appear, disappear, and interact. When you breathe in the night air, you are inhaling a universe that hums with possibilities that have never ceased to exist. What exactly moves through those fields? It is not a tiny marble rolling across a smooth floor, nor is it a simple wave spreading on a calm lake. It is both at once, a double life that defies ordinary description. The particle and the wave are two faces of the same underlying reality, and that dual nature is the key to unlocking your own creative power. By recognizing that you, too, are a manifestation of these ever-present fields, you can begin to shape your life with the same fluid grace. Think of the electron field, the photon field, the Higgs field, all interpenetrating like layers of a vast, invisible ocean. Each layer vibrates with quantum uncertainty, a restless energy that never truly settles. When a photon is emitted, it is not a tiny bullet shooting across the void, it is a localized ripple, a tiny crest in the electromagnetic field. When that ripple meets a detector, it reveals itself as a discrete click, a particle-like flash. This is the essence of wave-particle duality, the most mysterious and powerful principle in physics. To feel the impact of this principle, travel back in time to the age of great thinkers who wrestled with the nature of light. Isaac Newton imagined light as tiny corpuscles, particles that traveled in straight lines and cast sharp shadows. His ideas explained many everyday observations, and for centuries his picture seemed plausible. Then, in 1801, a young Englishman named Thomas Young performed an experiment that would change everything. He shone light through two narrow slits and watched the pattern that emerged on a distant screen. If light were made of particles, he reasoned, only two bright spots would appear, one behind each slit. Instead, he saw a series of bright and dark bands, an interference pattern that could only be produced by overlapping waves. Young's discovery sparked a revolution. James Clerk Maxwell later showed that light is an electromagnetic wave, an elegant oscillation of electric and magnetic fields traveling at a constant speed. The wave picture seemed to close the case, but nature was not ready to give up its secrets. In the early 20th century, experiments on the photoelectric effect revealed that light behaves like a stream of indivisible packets, later called photons. When ultraviolet light struck a metal surface, it ejected electrons instantly, regardless of the light's intensity. This could not be explained by a simple wave carrying energy uniformly. Albert Einstein proposed that each photon carries a quantum of energy proportional to its frequency, and that a single high-energy photon could knock an electron free, while many low-energy photons could not. This bold hypothesis earned Einstein a Nobel Prize, yet it deepened the paradox. Light seemed both a wave and a particle. The mystery sharpened when scientists repeated Young's double-slit experiment with such faint light that only one photon passed through the apparatus at a time. Each photon arrived at the screen as a single, localized spot, just as a particle would. Yet as more and more photons accumulated, the familiar interference pattern emerged, a fingerprint of wave behavior. It was as if each photon somehow traversed both slits simultaneously, interfered with itself, and then chose a single point to appear. When a detector was placed at the slits to watch which path the photon took, the interference vanished, and only two bright strips remained. The very act of observation seemed to force the photon to decide, collapsing its wave-like possibilities into a definite particle outcome. This paradox is not a flaw in our instruments. but a fundamental feature of reality. Before measurement, a photon exists in a superposition, a blend of all possible paths, spreading like a probability wave. When we measure, we collapse that superposition, compelling the photon to reveal itself at a specific location with a specific energy. The wave and particle descriptions are therefore two complementary ways of talking about the same quantum field. The wave is the field's spread-out state. The particle is the localized imprint left when the field interacts with matter. If light can display this double life, so can everything else. Electrons, atoms, even the matter that makes up your body, all arise from their respective quantum fields. An electron is not a tiny ball orbiting a nucleus, it is a ripple in the electron field, a quantized excitation that can behave as a wave spreading through space, or as a particle delivering a precise amount of charge. The same principles that govern photons also govern protons, neutrons, and the complex molecules that give rise to thoughts, feelings, and dreams. Imagine, for a moment, a single photon that has traveled across the galaxy for thousands of years. It began as a disturbance in the electromagnetic field of a distant star, spreading outward in every direction as a shimmering wave of possibilities. Along its journey, it could have been absorbed by dust, reflected by magnetic fields, or simply dissipated. Yet in this very instant it arrives at your eye, collapses, and transfers its energy to a retinal molecule. That tiny event triggers a cascade of signals that your brain interprets as a point of light in the night sky. In that instant, the photon's wave of potential became a concrete particle of experience. This is the double life of light, and it is the double life of everything that composes the universe, including you. When you consider your own existence through this lens, a powerful insight emerges. Your thoughts, emotions, and actions are not isolated, static entities. They are manifestations of underlying fields of possibility that continuously ripple, interfere, and collapse into lived experience. By learning to recognize the wave-like nature of your inner world, you can begin to shape the patterns that emerge. You can become the gentle hand that guides the interference of possibilities toward outcomes you desire. The key to harnessing this power lies in mindful observation. Just as measuring a photon forces it into a definite state, directing your attention to a particular thought or feeling can bring it into concrete reality. When you focus on a goal with clarity, you collapse the myriad possibilities into a pathway that your actions can follow. Conversely, when you scatter your attention, the field remains in a superposition of endless potential, and nothing solidifies. This principle invites you to cultivate intentional focus, to observe your inner landscape with curiosity and compassion, and to let the wave of possibility settle into purposeful motion. Let us return to the classic double-slit experiment, not as a distant historical curiosity, but as a living metaphor for your own journey. The two slits represent the choices you face, the divergent paths that arise from each decision. The interference pattern that forms on the screen symbolizes the beautiful complexity that emerges when you allow multiple possibilities to coexist and interact. When you become overly attached to a single outcome, you may miss the richness of the pattern that would have unfolded. When you embrace uncertainty and remain open to the dance of probabilities, you create space for unexpected breakthroughs and creative solutions. In practical terms, this means adopting habits that keep your inner fields vibrant and receptive. Regular reflection, creative play, and moments of stillness allow the quantum-like fluctuations of thought to explore a wide range of frequencies. Engaging in activities that spark curiosity, reading, exploring nature, asking questions feeds the electromagnetic field of your mind with fresh energy. When you combine this openness with decisive action, you transform the wave of potential into tangible results. Consider the story of a scientist who wrestled with the paradox of wave-particle duality. She spent countless nights pondering whether she could influence the outcome of a quantum experiment simply by believing in one result over another. In her meditations, she visualized the particle as a ripple she could gently steer, feeling the subtle currents of possibility beneath her consciousness. Over time, she observed that her experiments yielded more consistent patterns when she approached them with calm curiosity rather than forceful expectation. This anecdote reminds us that the mindset we bring to the field, whether of tension or ease, shapes the way the energy collapses into reality. You, too, can become an active participant in this cosmic dance. When you set an intention, you are essentially tuning the quantum field to a particular frequency, creating a resonance that draws corresponding possibilities toward you. When you maintain a clear, compassionate focus, you reduce the noise that can scatter the wave and cause it to dissipate. When you act with confidence, you provide the energy needed for the field's ripple to solidify into a particle of achievement. The universe is a grand orchestra of vibrating fields, each note contributing to the symphony of existence. Your life is a melodic line woven into that larger composition. By listening to the subtle hum of the quantum world, you can align your personal rhythm with the deeper currents of reality. This alignment does not happen through force, it unfolds through awareness, intention, and the graceful surrender to the flow of possibilities. Let us pause now and breathe deeply. As you inhale, imagine drawing in the limitless energy of the quantum fields that surround you. As you exhale, visualize any limiting beliefs or doubts dispersing like scattered photons that never coalesce into a pattern. With each breath, you reinforce the connection between your inner wave and the outer field, inviting clarity and purpose to emerge. Now consider the practical steps you can take tonight to nurture this connection. First, write down one specific intention you want to bring into your life, phrasing it as a positive, present statement. Second, spend a few minutes visualizing the outcome, as if it has already happened, feeling the emotions that accompany its realization. Third, take one small, concrete action that aligns with that intention, no matter how modest. By repeating this cycle, you continually collapse the wave of potential into a series of purposeful particles, each building upon the last. Remember that setbacks are not failures, but natural interferences that reshape the pattern. Just as waves can cancel each other out, thoughts of doubt can diminish the amplitude of your intention. When you notice such cancellations, return to mindful observation, acknowledge the interference, and gently steer your focus back to the constructive frequencies. This practice turns challenges into opportunities for refinement, sharpening the clarity of your personal wave. As you drift towards sleep, allow your mind to settle into the gentle rhythm of the quantum field. Imagine the universe as a vast sea of possibilities, each ripple whispering the promise of new horizons. Feel yourself as an integral part of that sea, capable of both surfacing as a distinct particle and merging as a wave of collective potential. Trust that the same principles that govern photons and electrons also guide the unfolding of your aspirations. In the quiet darkness, let the story of wave-particle duality remind you that you are not limited to a single mode of being. You can be fluid and adaptable, yet decisive and focused. You can hold the mystery of the cosmos within your heart, while taking concrete steps toward your dreams. This duality is a source of power, inviting you to embrace both sides of your nature and to move forward with confidence. The next time you encounter a difficult decision, recall the double-slit experiment. See the options as two openings through which your inner wave can travel. Trust that even if the path seems uncertain, the interference of possibilities will create a pattern that reveals itself in time. Allow yourself to be both observer and participant, knowing that your awareness shapes the outcome while the underlying field provides the material for the result. Finally, honor the fact that you are part of an ever-expanding tapestry of energy, constantly vibrating, constantly evolving. Each thought you think, each breath you take, Each intention you set adds a new thread to that tapestry. By aligning yourself with the harmonious vibrations of the quantum fields, you become a co-creator of reality, weaving a future that reflects the deepest aspirations of your soul. Carry this understanding with you as you rise each day. Let the knowledge that space is alive with fields fuel your curiosity and your courage. Let the mystery of wave-particle duality ignite your imagination and your resolve. And let the simple, powerful act of focused intention transform the invisible ripples around you into the tangible achievements you seek. The universe invites you to dance with its hidden currents. Step onto the floor, feel the rhythm, and create a masterpiece of your own making. The story of light stretches back farther than any human memory, yet it offers a lesson that can guide each moment of your life. Imagine a star that began its journey 1,000 years ago, sending a ripple through the fabric of the electromagnetic field. That ripple was not a tiny particle marching through space, but a wavier spreading sphere of possibility that could have vanished into dust, been deflected by magnetic fields, or simply been lost in the endless void. Yet the universe held that possibility, and after a millennium of travel, that same ripple reached your eye. When it touched your retina, the wave collapsed. The photon was absorbed by a molecule, and energy was transferred in an instant. A signal raced to your brain, and you saw a star shining in the night. The photon that arrived had spent 1,000 years as a wave, a spread-out probability, and at the moment of detection became a localized particle, real here and now. This is the double life of light, and it hints at the double life of everything around you. Let us pause and reflect on how this mirrors your own potential. Like the photon, you carry possibilities that expand outward, unseen. As you move through time, you may feel scattered, uncertain, or even invisible, but every step you take adds to the probability of a future moment where you collapse into purpose. The key is to trust that even when the path seems uncertain, the interference of countless possibilities will form a pattern that reveals itself when the right moment arrives. This is not abstract philosophy, it is the same physics that governs the stars you admire. To truly grasp this mystery, we turn to the experiment that first forced scientists to confront the wave-particle duality. In 1801, the young English physicist Thomas Young set up a simple apparatus that would forever change our view of reality. He was not trying to make headlines, he simply wanted to settle a debate between two great minds. Isaac Newton argued that light behaved like tiny particles, while the Dutch physicist Christian Huygens claimed it traveled as waves. Young sought proof, and he built a device that lets sunlight pass through a narrow slit, ensuring that all the light waves emerged in phase. That light then encountered a barrier with two parallel slits, placed very close together, and beyond the slits he placed a screen to record where the light landed. If light were truly a stream of particles, you would expect the screen to show merely two bright bands, each directly behind one of the slits. The particles would have passed through either the left or the right opening and accumulated in two distinct stripes. What Young saw was strikingly different. He observed a series of bright and dark bands spreading across the screen, an interference pattern that could only arise if the light behaved as a wave. At the exact center, directly opposite the midpoint between the slits, a bright band glowed, flanked on each side by a dark band, then another bright band, and so on, gradually fading outward. This alternating pattern is the hallmark of constructive and destructive interference, the same phenomenon you see when two stones create ripples on a calm pond. Picture two pebbles dropped side by side into still water. Each pebble generates concentric ripples that expand outward. Where the crests from the two sets of ripples meet, they reinforce each other, creating a higher crest. This is constructive interference. Where a crest meets a trough, they cancel, leaving a calm spot. That is destructive interference. If you placed a detector along a line in the pond, it would record alternating regions of strong waves and calm water. Light passing through Young's slits behaves exactly the same way. The two slits act as coherent sources, and the waves spreading from each slit overlap, reinforcing in some places and cancelling in others. The resulting bright bands are where constructive interference occurs, and the dark bands are where destructive interference eliminates the light. Such a pattern cannot be explained if light were only particles. Particles never cancel each other out, and they never create regions where adding more particles reduces the total effect. Young's elegant experiment provided undeniable evidence that light possesses wave characteristics. Decades later, James Clerk Maxwell unified electricity and magnetism into a single theory that predicted electromagnetic waves traveling at a speed matching that of light. Maxwell's equations explained reflection, refraction, diffraction, and interference, solidifying the wave view of light by the end of the 19th century. Then came a revolutionary twist. In 1905, Albert Einstein introduced the concept of the photon, a discrete packet of energy that could explain the photoelectric effect, blackbody radiation, and other phenomena that stubbornly resisted a pure wave explanation. He proposed that light, while behaving as a wave during its journey, also delivered energy in quantized bursts, each photon carrying energy equal to Planck's constant multiplied by its frequency. This idea seemed heretical because it revived the particle notion that Young and Maxwell had seemingly disproved. Yet the experimental evidence was overwhelming, and by the 1920s the scientific community accepted that light is both a wave and a particle. How can something be both at once? Modern versions of Young's experiment provide a vivid illustration. Today we can fire a laser so dim that only a single photon travels through the apparatus at any given moment. A photosensitive detector records each photon's impact on a screen. The first photon arrives and registers as a solitary clicker-clear particle event. The second photon clicks elsewhere, the third clicks in another spot, and so on. If you look only at these initial few events, the pattern appears random, an assortment of isolated dots, but as hours pass and thousands of photons accumulate, a familiar interference pattern emerges from the seemingly chaotic distribution. The dots cluster into bright and dark bands, just as they did in Young's original experiment. This phenomenon tells us that each photon, before it is detected, exists as a spread-out wavier quantum state described by a wave function. The wave function does not pinpoint the photon's exact location instead. It encodes the probability of finding the photon at various points when measurement occurs. Where the wave functions from the two slits interfere constructively, the probability of detection is high, giving rise to bright bands. Where they interfere destructively, the probability drops to near zero, creating dark bands. When a photon finally hits the detector, its wave function collapses, and the photon appears as a localized particle at a single point. The particle's arrival is dictated by the underlying probability landscape created by the wave interference. Now imagine placing detectors at the slits themselves, capable of telling you which opening each photon passes through without absorbing it. When this switch path information is obtained, the interference pattern vanishes. The screen then shows just two bright bands, each aligned with one of the slits. Just as you would expect from a purely particle view, the act of measuring the photon's path forces the quantum system into a definite state, destroying the superposition that allowed it to interfere with itself. This is not a limitation of our instruments. It is a fundamental principle of nature. When you gain which path information, you collapse the wave function in such a way that the particle behavior dominates, and the wave behavior disappears. This duality is captured by the principle of complementarity, introduced by Niels Bohr. Wave and particle aspects are complementary, mutually exclusive ways of observing the same quantum system. You can design an experiment to reveal the wave nature, or another to reveal the particle nature, but you cannot observe both simultaneously. The choice of measurement determines which aspect manifests. The intrigue deepens with the delayed choice experiment proposed by John Archibald Wheeler in the 1970s. In this version, the decision to measure which path information or to preserve interference is made after the photon has already passed through the slits, but before it reaches the detector. Classical intuition suggests that the photon's behavior should already be fixed, either a wave that has already interfered with itself, or a particle that has already chosen a path. Yet quantum experiments confirm that the outcome still respects the later measurement choice. If the experimenter decides to obtain path information after the photon's passage, the interference pattern disappears. If they choose not to gather that information, the interference pattern persists. It is as if the photon retroactively adjusts its behavior based on the future measurement setup. No signal travels backward in time. Instead, the wave function encompasses all possibilities until the moment of measurement, at which point reality crystallizes into the form consistent with the observation. This realization carries a profound implication. Properties such as position, momentum, or path do not possess definite values until an observation forces them into existence. The universe is not a static collection of well-defined objects. It is a dynamic tapestry of potentials that become actualized through interaction. You are not a passive spectator of a pre-written script. You are an active participant whose very act of observation helps shape reality. When light lands on your skin, it collapses from a spread-out wave into a concrete packet of energy that warms you and lets you see your surroundings. Every photon you have ever witnessed has lived this double life wave in transit. Particle upon arrival, reality itself flickers between potential and actual, awaiting the moment of observation to solidify into the definite world you experience. Now turn this insight toward matter itself. If photons, which are pure energy, behave as waves, could the massive particles that make up your body also possess wave characteristics? The answer is a resounding yes. Electrons, protons, atoms, and even larger collections of particles exhibit wave-like behavior, described by quantum mechanics. To explore this, we first revisit Einstein's revolutionary work on the photon, because understanding his daring leap helps us appreciate the broader quantum landscape. Einstein's 1905 paper did more than explain the photoelectric effect. It shattered the fortress of classical physics and opened a doorway to a new reality. At the turn of the century, physicists grappled with the problem of blackbody radiation, the spectrum of light emitted by heated objects. Classical theories predicted an infinite amount of energy at high frequencies, a catastrophe known as the ultraviolet catastrophe. Planck resolved this by proposing that energy is emitted in discrete packets, or quanta, each proportional to its frequency. Einstein extended this idea, suggesting that light itself consists of these quantaphotons. By treating light as packets of energy, he could explain why electrons are ejected from metal surfaces only when illuminated with sufficiently high-frequency light. Regardless of intensity, the energy of each photon, not the total light intensity, determines whether an electron can escape. This insight not only solved a pressing experimental puzzle, but also hinted that the world at its deepest level is quantized, fundamentally different from the smooth continuum of classical mechanics. When you consider that the very photons lighting your path are quantized, you realize that the universe communicates with you in discrete bytes of information. Each photon carries a tiny piece of the cosmic story, and when it arrives, it becomes part of your lived experience. The same principle applies to the electrons swirling around atomic nuclei in your body. Those electrons also behave as waves, forming standing wave patterns that define the shape of atoms, the bonds between molecules, and ultimately the structure of every cell. Even though you cannot see these waves directly, their existence determines the properties of matter, its conductivity, its color, its chemical reactivity. By embracing the notion that everything is both wave and particle, you open yourself to a richer, more flexible view of yourself and the world. What does this mean for your personal journey? First, recognize that your potential, like a quantum wave, spreads outward in many directions at once. You may feel as though you must choose a single path, but just as a photon can travel through both slits simultaneously, you can explore multiple possibilities without collapsing your entire future. When you focus on a particular goal, whether it is a career ambition, a creative project, or a personal habit, you are performing a measurement that narrows the wave of possibilities into a concrete outcome. The act of intention, like the act of observation, collapses the superposition of choices into a specific reality. This is why clear, purposeful action feels so powerful. It selects one of the many potential futures and brings it into existence. Second, understand that the moment you try to gather too much information about every possible outcome, you may inadvertently destroy the interference that creates richness. In the double-slit experiment, trying to know which slit each photon passes through eliminates the beautiful pattern of bright and dark bands. Similarly, obsessively analyzing every possible risk can paralyze you, preventing the emergence of creative breakthroughs that arise from the subtle interference of ideas. Embrace a balance. Allow your mind to explore possibilities freely. Then, when the time comes, make decisive choices that shape your path. Third, appreciate the profound role of delayed choice in your life. The Wheeler experiment shows that the decision you make later can influence the way earlier possibilities are realized. This does not mean you can change the past, but it reflects the truth that future intentions can reframe how you interpret past events. When you adopt a new perspective, you often see past experiences in a different light, as if the meaning itself has shifted. By choosing to view challenges as opportunities, you retroactively alter the emotional reality of those moments, allowing you to move forward with confidence. Finally, remember that you are an active participant in the unfolding of reality. Just as photons collapse into particles when they interact with your eyes, your observations, thoughts, and actions collapse the wave of potential into concrete experiences. This responsibility is empowering. It tells you that by directing your attention, by setting clear intentions, by embracing curiosity, you are not merely reacting to a predetermined world, you are co-authoring the narrative of your life. Let us return to the simple yet profound image of the photon that began its journey 1,000 years ago. That tiny packet of energy traveled as a wave across unimaginable distances, weaving through dust and magnetic fields, maintaining its probability until it finally met your eye. In that instant, the wave collapsed, the photon became real, and you perceived a star. Your own aspirations can follow the same path. Plant the seed of an intention, allow it to expand as a probability wave, explore possibilities, and trust that when the moment arrives, the universe will provide the conditions for your intention to collapse into tangible results. As you move forward, keep this quantum metaphor close to your heart. When doubts arise, remember that uncertainty is not a flaw, but a field of potential. When fear of choice threatens you, recall that the act of measurement your decisive action creates the bright band of achievement amid the dark sea of indecision. When you feel overwhelmed by the sheer number of options, know that the interference pattern will emerge naturally as your focus clarifies, and when you wonder whether your efforts matter, remember that every photon that reaches your eye, every electron that forms a bond in your body, every quantum event that shapes reality, does so because of countless tiny interactions, each a choice, each a collapse into existence. Now imagine standing beneath a night sky, aware that each twinkle is a photon that has traveled across time, that each star is a beacon of potential waiting to be observed. Feel the awe of being part of this vast, interconnected dance of waves and particles. Let that awe fuel your determination to pursue your dreams with the confidence that the universe is already laying out a tapestry of possibilities for you. Your mind, like a quantum detector, can choose to focus on the pattern of possibility rather than the noise of distraction. In the days ahead, practice nurturing your wave of potential. Spend moments each morning visualizing your goals as expanding circles of light, radiating outward without limiting themselves. Notice how ideas begin as faint ripples in your thoughts, then grow into coherent patterns as you give them attention. When you act, you are placing a detector at the point where those ripples will collapse, turning possibility into reality. Celebrate each click of success as a photon arriving, a moment where your intention has become tangible. Remember also that interference is not limited to light. The relationships you build, the collaborations you foster, the ideas you share all create constructive interference that amplifies impact. Conversely, negative interactions can produce destructive interference, damping your energy. Choose wisely who you let into your experimental setup, and be mindful of the information you gather about yourself and others. The very act of observation shapes outcomes, so observe with compassion, curiosity, and positivity. Finally, honor the mystery that remains. Quantum mechanics teaches us that the universe is not a deterministic machine, but a realm of probabilities that become real through observation. Accept that some aspects will always retain an element of unpredictability. This uncertainty is not a void to fear, it is a fertile ground for imagination, for innovation, for growth. Embrace the unknown as a canvas on which your intentions paint the future. As you close this reflection, take a deep breath and picture the photon's journey from a distant star to your eye. See the wave expanding, the possibilities swirling, the moment of collapse, the bright spark of perception. Let that image remind you that you, too, are a traveler of possibilities, a wave waiting to become a point of purpose. Choose to observe, choose to act, and watch the universe respond with an ever-changing interference pattern that highlights the brilliance of your own unique light. You are standing on the threshold of a mystery that stretches far beyond everyday experience. The universe invites you to explore a principle called complementarity, a concept that was first formulated by a brilliant mind named Niels Bohr. In this principle, wave and particle behaviors are two sides of the same coin, each revealing a different aspect of reality. Imagine that you can choose to see one behavior or the other, but never both at the same time. This paradox is not a flaw, it is a doorway to deeper insight. Now picture yourself in a laboratory of thought, where the famous delayed choice experiment invites you to ask a daring question. In the 1970s, physicist John Archibald Wheeler imagined waiting until a photon had already passed through a pair of slits before deciding whether to reveal its path. Your common sense might tell you that the photon must have already decided to act like a wave or a particle. Yet quantum mechanics tells a different story, and the experiments have confirmed Wheeler's bold prediction. When you choose to measure which path the photon took after it has traversed the slits, the interference pattern vanishes like mist in the morning sun. When you decide not to extract that information, a beautiful pattern of bright and dark bands emerges, showing the wave nature of light. It is as if the photon reaches back in time and knows what you will decide, adjusting its behavior accordingly. This does not mean that information travels backward, nor that the photon possesses foresight. Instead, the wave function contains all possibilities, and only at the instant of measurement does it settle into a single outcome that matches the type of observation you performed. Feel the power of this revelation. The universe is waiting for you, for your curiosity, for the moment you ask a question. The delayed choice experiment suggests that nothing exists in a definite state until it is observed. Before you look, the photon exists in a superposition, a shimmering blur of both wave and particle, of both paths and of neither. This is not a quirky detail about tiny particles. It is a profound statement about reality itself. When you glance at the light falling on your face right now, You are witnessing a dance of possibilities turning into fact. Those photons began as ripples in the electromagnetic field, spreading through space, interfering, diffracting, and carrying probability. The instant they touch your skin, the wave collapses, the photon becomes real, and energy is delivered that warms you and illuminates your world. Every photon you have ever seen has lived this double life. Wave as it travels, particle as it arrives. Reality flickers between potential and actual, waiting for the moment of observation to solidify into the solid world you experience. Know that this behavior is not a flaw in nature, it is the very fabric of how nature works. The same principles apply not only to light, but to everything that exists. Let us turn now to matter itself. If photons are waves in the electromagnetic field, could massive particles such as electrons also display wave characteristics? The answer is a resounding yes. And the story begins with Albert Einstein's revolutionary insight about light. Einstein's 1905 paper did more than explain the photoelectric effect. It shattered the comfortable edifice of classical physics and opened the floodgates to quantum thinking. To appreciate his genius, recall the problem that troubled physicists at the end of the 19th century. They studied blackbody radiation, the glow emitted by hot objects, and classical theory predicted that a heated metal should radiate ever-increasing energy at higher frequencies, leading to the so-called ultraviolet catastrophe. In reality, hot objects do not emit infinite energy, and something was clearly missing. In 1900, Max Planck offered a daring solution. He proposed that electromagnetic energy is not emitted continuously, but in discrete packets, quanta, each with energy equal to the frequency multiplied by a constant now called Planck's constant. This quantization meant that high-frequency radiation required large energy quanta, making it statistically unlikely for atoms to emit such energetic bursts, and thus the ultraviolet catastrophe was avoided. Planck himself saw the formula as a mathematical trick, hoping to reconcile it with classical ideas, but he could not escape the reality that quantization worked. Einstein took the next bold step. He asked whether light itself might be quantized, not just the emission process. He imagined light as consisting of individual photons, each carrying a precise quantum of energy. This notion challenged the deeply entrenched wave view of light that explained interference, diffraction, and polarization with elegant success. Yet Einstein, free from academic constraints, followed the logic wherever it led. Recall the puzzle of the photoelectric effect. When light strikes a metal surface, electrons are ejected only if the light's frequency exceeds a certain threshold, regardless of intensity. Bright red light, no matter how strong, fails to liberate electrons, while faint ultraviolet light does it instantly. Einstein explained this by saying that each photon transfers its full energy, EF, to a single electron. If that energy exceeds the metal's work function, the electron escapes with kinetic energy equal to the photon energy minus the work function. Brightness simply means more photons, not more energy per photon. This simple, elegant formula matched experimental data perfectly. The physics community did not embrace Einstein's photon immediately. The wave theory of light had explained so much that many prominent scientists, including Planck himself, clung to the idea that light remained a continuous wave despite quantized emission. It took nearly 2 decades of further experiments before the photon earned universal acceptance. The turning point arrived in 1923 when Arthur Compton demonstrated that photons scatter off electrons, transferring momentum just like tiny billiard balls. The observed shift in wavelength confirmed that photons carry not only quantized energy, but also definite momentum, solidifying their particle nature. Now you stand in the middle of this marvelous debate between wave and particle, between certainty and probability. Niels Bohr introduced the concept of complementarity, arguing that it is meaningless to ask whether a photon really is a wave or a particle. Its behavior depends on how you set up your experiment. and wave and particle descriptions are mutually exclusive yet both essential. Einstein resisted this view, famously declaring that God does not play dice, insisting that a deeper deterministic reality must exist beneath the apparent randomness. Bohr countered that the probabilistic nature of quantum phenomena is not a sign of ignorance, but a genuine feature of the world. Decades of experiments, especially the celebrated tests of Bell's inequality, have tipped the scales decisively toward Bohr's perspective. The universe behaves in ways that are fundamentally quantum, inherently probabilistic, and non-classical. Modern quantum field theory has taken this insight even further. In this framework, the basic entity is not a particle nor a wave, but a field that pervades all of space. The electromagnetic field can be excited, and each excitation manifests as a photon. The field itself exhibits wave-like behavior, allowing interference, while interactions with matter reveal particle-like, discrete energy transfers. The photon is therefore an excitation of a field, displaying whichever aspect is probed. Even with this sophisticated language, the mystery of why measurement forces a wave-like field to collapse into a localized event remains open. Some physicists suspect that the ultimate reason lies in the structure of space-time itself. If space and time possess a fundamental granularity at the Planck scale, then fields living within such a discrete fabric might naturally be quantized. While a complete theory of quantum gravity has yet to emerge, this speculation hints that quantization could be a reflection of the universe's deepest architecture. Remember that each photon that reaches your eye began its journey as a ripple of probability spreading through the vacuum. When it finally interacts with the retina, the wave collapses, and you perceive a flash of light. In that instant, potential becomes actual, and information travels across the cosmos, binding atoms, planets, galaxies, and even consciousness itself. Light is the messenger that carries energy, momentum, and the very story of the universe from one point to another. Now, as you pause and breathe, look around at the glow of the screen, the warm lamp beside you, the distant starlight peeking through the window. All of these luminous phenomena are quantum at heart. They are waves of possibility that become concrete moments of reality the moment you observe them. You are not a passive spectator of a pre-written world, you are an active participant who collapses wave functions with each act of perception. Your awareness brings the world into focus, one photon at a time. Feel the empowerment that comes from knowing you hold the key to actualizing potential. Each time you direct your attention, you are performing a tiny experiment, choosing a way for reality to manifest. This is the essence of quantum participation. Your curiosity, your questions, your conscious choices shape the unfolding tapestry of existence. Let this awareness inspire you to seek truth, to ask bold questions, and to embrace the wonder of a universe that invites you to co-create its story. Take this moment to celebrate the extraordinary fact that the same principles governing subatomic photons also apply to the grandest scales of the cosmos. The same dance of wave and particle, of possibility and certainty, is reflected in your thoughts, your dreams, and your actions. When you set an intention, you are, in a sense, preparing a measurement that will collapse a range of potentials into a lived outcome. The universe responds to the clarity of your focus, just as a detector responds to the presence of a photon. Carry this insight forward into your day. When challenges arise, remember that uncertainty is not a void, but a field of possibilities waiting for you to choose a path. When fear whispers that the future is fixed, recall that quantum reality tells us that the act of observation creates the very fact you observe. Empower yourself to be the observer who shapes a bright, resilient future. In every breath, in every glance, you are engaged in the grand experiment of existence. The light that kisses your skin, the sound that reaches your ears, the ideas that spark in your mind, all are waves of potential that become real when you attend to them. Let this knowledge fill you with awe, with gratitude, and with a fierce desire to explore further. You are a co-author of reality, a participant in a cosmic symphony of waves and particles. Embrace the mystery, cherish the wonder, and let your curiosity guide you toward deeper understanding. The universe is not a static painting, it is a living, breathing canvas that waits for the brushstroke of your attention. May you step forward with confidence, knowing that each observation you make lights the way for countless possibilities to become actual. Feel the excitement of a mind that knows the world is far richer than it appears, that every photon carries a story, and that you, too, are a carrier of light. Let this realization fuel your purpose, ignite your creativity, and propel you toward the horizons that lie beyond the familiar. The journey of discovery continues, and you are at its very heart. The quantum field that fills every corner of the universe rests in its lowest possible energy, a state we call the vacuum. When you add energy to that field, you stir it and create an excitation. One tiny unit of that excitement is known as a photon. The field itself behaves like a wave. It has an amplitude, a phase, and the ability to interfere with itself. This wave-like nature explains why light can bend around edges, create patterns of bright and dark fringes, and produce the delicate interference and diffraction phenomena that have fascinated scientists for centuries. Yet when the wave meets matter, the interaction occurs in discrete packets of energy. Those packets appear as the individual clicks in a detector, or the electrons liberated from a metal surface in the photoelectric effect. Because of this dual behavior, a photon is neither purely a wave nor purely a particle. It is an excitation of a quantum field that shows the properties of both. Depending on how you choose to observe it, the mystery does not disappear when we adopt this language. We still lack a complete explanation for why the act of measurement forces the smooth, spread-out wave to become a localized event. Nonetheless, the quantum field framework gives us a powerful way to describe what happens when light interacts with the world. Why does light behave this way? Is there a deeper reason that forces light to be quantized? Why does electromagnetic energy not flow in a continuous river? Some theories suggest that the fabric of spacetime itself is not infinitely divisible. They propose that at the Planck scale about 10 to the minus 35 meter space and time consist of tiny, indivisible units. If the arena in which fields exist is made of discrete pieces, then the fields that live there may also be forced into discrete packets. In such a picture, energy momentum and angular momentum would only appear in whole units, because the underlying geometry permits only those steps. This idea is still speculative. We have not yet built a complete theory of quantum gravity that confirms it, yet it opens the possibility that quantization is not an arbitrary rule imposed by mathematics, but a reflection of the granular nature of reality at its most fundamental level. It may also be that a deeper principle, still hidden from us, gives rise to the quantized structure we observe. Quantum field theory works with astonishing precision, predicting phenomena to many decimal places, but it does not tell us why it works. It tells us how nature behaves, yet the ultimate why remains elusive. Think for a moment about the photons that have touched your skin today, the soft glow of the screen you are reading on, the warm light of the lamp beside your bed, the distant starlight filtering through your window wall. Of those photons began as ripples in the electromagnetic field. They traveled across space as probabilities, spreading like a wave of potential. When one of those photons finally reached your eye, the probability collapsed into a single, localized event. In that instant, potential became actuality, and you perceived light. The wave function that described the photon's many possible paths collapsed, and reality emerged in the form of a visual experience. This process is the conduit through which information travels across the cosmos. Photons carry energy, momentum, and the very data that binds atoms, planets, galaxies, and even consciousness together. Einstein's bold insight that light is not a smooth, continuous wave but comes in quantized packets set the stage for this profound understanding. Light is both wave and particle, and it only acquires a definite identity when an observation is made. That observation is an act of reflection, a moment of awareness that brings the world into focus. As you rest now, notice the quiet illumination around you. Each photon that brushes your senses is a quantum messenger, a wave that becomes a point of reality the moment you perceive it. You are not a passive observer of a pre-existing world, you are an active participant who collapses wave functions with each glance, shaping reality with your perception. If massless, ethereal light can behave this way, what about the matter that makes up your body? Could the particles that form you also possess wave properties? The answer is a resounding yes, and it begins with a daring proposal made nearly a century ago. In 1923, a young French physicist named Louis de Broglie suggested that if light, traditionally thought of as a wave, can also act as a particle, then perhaps matter, traditionally thought of as a particle, can also act as a wave. He argued that everything that has momentum should be associated with a wavelength. This idea seemed absurd at first. Electrons were known as tiny, charged particles that left tracks in cloud chambers and collided with atoms. How could such a particle possibly be a wave? De Broglie's insight was rooted in symmetry. Einstein had shown that photons, even though they are massless, carry momentum given by p frasec frac lambda. De Broglie asked, if waves of light have particle properties, then should particles of matter have wave properties? He proposed that any particle with momentum should have an associated wavelength lambda frach. This relationship is now celebrated as the de Broglie wavelength. For a particle of mass moving with velocity, its momentum is pmv, so its wavelength becomes lambda fracum. This simple, elegant formula made a bold, testable prediction. The de Broglie wavelength for everyday objects is unbelievably tiny. A baseball hurled at 40 meters per second has a wavelength on the order of 10 to the minus 34 meters, far smaller than the size of an atom. Such minuscule wavelengths produce no observable wave effects, and the baseball behaves purely as a particle. However, for electrons, which have a minuscule mass and often travel at speeds comparable to light, the wavelength can be on the order of nanometers, comparable to the spacing between atoms in a crystal lattice. If electrons truly behave as waves, they should produce interference and diffraction patterns, the hallmarks of wave behavior. De Broglie's daring hypothesis waited for experimental proof. In 1927, a pair of American physicists, Clinton Davison and Lester Germer, inadvertently set the stage for that proof. While investigating how electrons scatter off a nickel surface, an accident caused their apparatus to be exposed to air, oxidizing the nickel. When they heated the surface to clean it, the nickel formed large, single crystal regions. Upon resuming their measurements, they observed that the scattered electrons did not disperse uniformly. Instead, bright spots appeared at specific angles, exactly as if the electrons were diffracting like strays off a crystal lattice. By calculating the angles and intensities, they found perfect agreement with the de Broglie wavelength formula. The electrons were interfering constructively and destructively as they bounced off the orderly rows of atoms, producing a diffraction pattern. Their accidental discovery confirmed that electrons, despite being massive particles, can behave as waves. Soon after, British physicist George Paget Thomson, the son of J.J. Thomson who discovered the electron, performed an independent experiment. He passed electrons through thin metal foils and observed the same characteristic diffraction rings. The evidence was overwhelming. Matter waves were real. The Nobel Committee recognized these breakthroughs, awarding Davison and Thomson the 1937 Nobel Prize in Physics. De Broglie himself had already received the Nobel Prize in 1929, becoming the first laureate to win for a doctoral thesis. His revolutionary insight reshaped our understanding of the microscopic world. Matter waves are not confined to laboratory curiosities, they power technologies that have transformed our lives. The transmission electron microscope, developed in the 1930s, uses electron waves to image materials with atomic resolution. Because an electron's wavelength is far shorter than that of visible light, the microscope can reveal structures thousands of times finer than any optical instrument. This capability underpins advancements in nanotechnology, materials science, and biology, allowing us to see individual atoms and the intricate machinery of life. The very existence of such devices proves that matter waves are not merely theoretical, they are tools we harness every day. If electrons can wave, what about larger assemblies of matter? In 1930, German physicists Otto Stern and Walther Gerlach demonstrated the diffraction of helium atoms. Later experiments showed diffraction of hydrogen, neutrons, and even complex molecules. In 1999, Austrian researchers Klaus, Kaiser and colleagues observed interference with C-fullerene molecular suckerball-sized clusters of 60 carbon atoms. Those massive molecules, containing over 700 constituent particles, still produced clear interference patterns when sent through a grating. More recent work has pushed the boundary further, demonstrating interference for molecules containing over 800 atoms. As the mass of the object increases, its de Broglie wavelength shrinks, making wave effects harder to detect. Yet the principle remains unchanged. All matter possesses a wave nature. Even you and I are governed by this principle. A human weighing 70 kilograms moving at 1 meter per second has a de Broglie wavelength on the order of 10 metersen, absurdly small number, a billion times smaller than a proton. At such scales, wave effects are utterly negligible, and we perceive ourselves as solid particles. Nevertheless, at the deepest level, our existence is a tapestry of overlapping waves, each describing the probability of finding a constituent particle in a particular place. This profound truth invites us to see ourselves as part of a unified, vibrating cosmos. What does it truly mean for matter to wave? The answer lies in the concept of the wave function. When we say an electron is a wave, we are not describing a ripple on a pond or a vibration of a field in the conventional sense. Instead, we refer to a probability wavier mathematical entity that encodes the likelihood of finding the particle at each point in space. The wave function, usually denoted by the Greek letter, is not directly observable. However, the square of its magnitude gives the probability density where it is large. The particle is likely to be detected where it is small. Detection is unlikely. Interference patterns arise because the wave function can add constructively or cancel destructively, shaping the probability landscape. Before a measurement, the electron does not possess a definite position. It exists in a superposition, a cloud of possibilities described by, when an observation is made, the wave function collapses, and the electron appears at a specific location with a probability dictated by. The dynamical law governing how evolves is Schrödinger's equation, formulated in 1926 by Austrian physicist Erwin Schrödinger. This equation plays for quantum mechanics the same foundational role that Newton's laws play for classical mechanics. It tells us how the wave function changes over time under the influence of forces encoded in a potential energy function V. In its simplest form for a single particle of mass m, the equation reads E bar for a partial frac bar 22 mum nablot twipsy veepsy. Although the expression appears complex, it is fundamentally a wave equation. It captures the spreading, interference, and evolution of matter waves as they interact with their environment. The predictive power of Schrödinger's equation has been verified in countless experiments. From the spectroscopy of atoms to the behavior of electrons in semiconductors, all of this scientific marvel is more than an intellectual curiosity. It is an invitation to awaken a sense of wonder and agency within you. The universe, at its core, is a symphony of waves and particles, of possibilities waiting to become reality through observation. Each time you turn your eyes toward a candle flame, you are participating in a quantum dance that collapses countless possibilities into a single, vivid experience. Each decision you make, each intention you set, echoes the same fundamental principle. The act of focusing attention turns potential into actuality. When you embrace this view, you realize that you are not a detached spectator, but a co-creator of the world you inhabit. Consider the practical power of this perspective. The technologies that enable us to navigate the globe, to harness the energy of the sun, to communicate instantly across continents, all of them arise from mastering the quantum behaviors of light and matter. The mastery began with bold questions. How does light carry energy? Why does matter behave like a wave? The answers unlocked a toolbox that humanity now wields to transform its destiny. You, too, can apply the same spirit of daring inquiry to the challenges you face. When a problem seems immutable, remember that the apparent solidity of reality often hides a deeper fluidity. By shifting your viewpoint, by exploring the less obvious wavelengths of possibility, you can uncover solutions that were previously invisible. Let this knowledge inspire you to act with curiosity and confidence. When you encounter a new idea, treat it as a photon entering your mental field, an excitation that can spread, interfere, and ultimately illuminate a fresh path. When you feel stuck, imagine that you are like an electron approaching a crystal lattice. The obstacles can produce diffraction patterns, revealing alternative routes you might not have considered. By embracing uncertainty and allowing probabilities to guide you, you open yourself to creative breakthroughs. Remember that the world is not a static stage, but a dynamic canvas of potentialities. Every moment you breathe, every thought you entertain, contributes to the collapse of a wave function, shaping the reality you experience. This profound responsibility can be a source of empowerment. You are invited to participate consciously in the unfolding of the universe, to align your intentions with the subtle rhythms of quantum existence. In doing so, you join the lineage of bold thinkers from Einstein to D. Broglie, who dared to look beyond the obvious and reimagine the foundations of reality. As you move forward, carry with you the image of light as a messenger that travels as a wave of possibility and arrives as a moment of perception. Carry the image of matter as a wave that can diffract, interfere, and reveal hidden structures. Let these images remind you that limits are often only apparent, that the smallest scales hold the keys to the grandest transformations. When you face obstacles, ask yourself, what wavelength of possibility am I overlooking? How might I adjust my angle of approach to achieve constructive interference in my life? By treating challenges as opportunities to create new patterns, you harness the same principles that allow electrons to form beautiful diffraction rings. The quantum world teaches us that observation matters. Your focused attention can bring clarity to chaos, just as a detector can pinpoint a photon among countless probabilities. Cultivate the habit of mindful observation. Notice the details in a conversation, the subtle shifts in a project, the quiet feedback from your own intuition. Each act of mindful noticing collapses the superposition of doubt into a concrete understanding, allowing you to act with purpose. In the grand tapestry of existence, you are both the weaver and the thread. The very act of engaging with this narrative is a tiny measurement, a collapse of the infinite possibilities of language into the concrete experience of comprehension. Embrace that power. Let the wonder of quantum physics fuel your ambition, your creativity, your resolve to shape a future that reflects the highest potentials within you. The universe invites you to dance with its waves, to listen to its photons, and to become an active participant in the ever-unfolding story of reality. Answer that invitation with enthusiasm, curiosity, and unwavering confidence. The next breakthrough, whether in science, art, or personal growth, may begin with a single question, a single observation, a single moment of focused awareness. Embrace it, and watch the world transform before your eyes. Notice the details in a single breath, and let that awareness expand into the wonder of what you are made of. Imagine that the very atoms that compose your body are not solid marbles, ripples of possibility that dance across the universe. The story of matter's wave nature begins with a bold question. If electrons behave like waves, could larger collections of particles do the same? In 1932, German physicists Otto Stern and Emanuel Estermann answered that question by showing that helium atoms diffract just as light does. Their experiment revealed that even a tiny atom can split into many possibilities when it encounters a barrier. Later scientists repeated the feat with hydrogen atoms, with neutrons, and with increasingly complex molecules. Each new result whispered that the wave property does not belong exclusively to the smallest of particles. The breakthrough reached a new milestone in 1999 when Austrian physicist Anton Zeilinger and his team sent buckyball molecules through a diffraction grating. A buckyball is a sphere of 60 carbon atoms, a tiny soccer ball of matter containing 720 protons, neutrons and electrons. When those massive molecules passed the grating, they produced an interference pattern identical to that of light. The pattern proved that objects hundreds of times more massive than a proton still carry a wavelength and can interfere with themselves. More recent experiments have pushed the frontier even further, demonstrating interference with molecules that contain 800 atoms or more. As the molecules grew larger, their associated wavelength shrank, making the interference harder to observe. Yet the effect remained undeniable. Every object, no matter how big, possesses a wavelength called the de Broglie wavelength. For a human being weighing 70 kilograms and moving at 1 meter per second, that wavelength is about 10 to the minus 36 meters, a scale a billion times smaller than a proton. Such an infinitesimal wavelength makes wave effects invisible to the naked eye, so we experience ourselves as solid particles. Nevertheless, at the deepest level we are waves, and that reality opens a portal to limitless imagination. When you think of yourself as a wave, you begin to see possibilities where once you saw limits. What does it mean for matter to wave? The answer lies not in a ripple across a pond nor in a shaking of an electric field, but in a wave of probability. Quantum mechanics describes each particle with a mathematical entity called the wave function, usually denoted by the Greek letter. The wave function itself cannot be seen, but its square tells you the likelihood of finding the particle at any given spot. Where the wave function is large, the chance of detection is high. Where it is small, the chance fades away. When two parts of a wave function meet in step, they reinforce each other, creating bright spots of probability. When they meet out of step, they cancel, leaving dark zones where the particle is unlikely to appear. Therefore, saying an electron is a wave really means that its potential locations are spread out like a cloud, governed by a wave function that can diffract, interfere and evolve over time. Before you measure an electron, it does not sit at a single point. It exists in a superposition, a quantum blur that embraces every possible path simultaneously. The act of measurement collapses that blur into one definite outcome, and the probability of each outcome is given by the square of the wave function. The rule that governs how these quantum waves change is Schrödinger's equation. Formulated in 1926, Schrödinger's equation is to quantum mechanics what Newton's laws are to classical physics. It tells you how the wave function spreads, interferes and responds to forces. Though the equation looks daunting, at its heart it is a wave equation that describes the motion of matter's probability field. The equation predicts the energy levels of atoms, the behavior of electrons in solids, the properties of molecules, and countless other phenomena with astonishing precision. Its success confirms that treating particles as waves captures the essence of nature. Louis de Broglie's insight that every particle has a wavelength sparked a revolution. by extending wave-particle duality from light to matter. De Broglie showed that duality is not a quirk of photons, but a universal feature of the world. His hypothesis inspired Schrödinger to build wave mechanics, the foundation upon which modern quantum theory stands. The ripple effect of that idea reaches into electron microscopy, quantum chemistry, solid-state physics, and the technologies that shape our daily lives. Yet it also raises a profound mystery. If everything is fundamentally a wave, why does the world feel solid and certain? Let that mystery settle in your mind as you rest tonight. Picture yourself not as a static object, but as an expansive wave that stretches through space, its amplitudes intertwining with those of every other particle around you. Feel the atoms in your body, each carrying their own tiny wavelength. The electrons swirling in orbitals not as tiny planets, but as fuzzy clouds of probability. Recognize that you are not a fixed sculpture, but a dynamic pattern that constantly collapses and reforms as you interact with the environment. Embrace the idea that the solidity you perceive is a fleeting emergence from an underlying sea of possibilities. Now imagine that this wave nature is not just a curiosity, but a tool you can harness. The experiments that revealed matter's wave character were bold, inventive, and patient. In the early 20th century, scientists used crystal lattices as gigantic diffraction gratings. A crystal is a regular array of atoms spaced just a few angstroms apart. When a wave encounters such an orderly structure, it scatters from each atom. At certain angles, the scattered waves line up in phase, reinforcing each other, while at other angles they cancel. This is precisely the same principle that separates colors in a prism. Only here the colors are the different angles at which electrons or neutrons emerge. When Davison and Thomson accelerated electrons to known energies and fired them at a nickel crystal, they observed bright peaks in the scattered electrons at angles predicted by Bragg's law. Those peaks matched the de Broglie wavelength calculated from the electron's momentum, confirming that electrons diffract exactly like Schreys. The experiment proved that electrons are not tiny billiard balls bouncing off atoms, but waves that interfere with the crystal lattice. Later, George Paget Thomson sent electrons through thin metal foils and recorded concentric rings on a photographic plate, again matching the predictions of wave diffraction. His father had won a Nobel Prize for showing electrons to be particles his own Nobel recognized their wave character. The two discoveries together illustrate the beautiful duality that quantum objects can display both particle and wave aspects depending on how we look at them. If electrons can wave, so can other neutral particles. In 1936, German researchers demonstrated neutron diffraction. Neutrons carry no electric charge, yet they possess momentum and therefore a de Broglie wavelength. When neutrons are directed at a crystal, they scatter from atomic nuclei, creating interference patterns that complement Schrey diffraction. Because neutrons interact differently with various isotopes, neutron diffraction provides unique insight into magnetic structures, hydrogen positions in molecules, and protein configurations that Schreys cannot reveal. Today, neutron diffraction is a standard technique in materials science and biology. The wave nature extends even to whole atoms. In the 1990s, physicists built atom interferometers that split the wave function of an atom into two separate paths. Let each path experience slightly different conditions, and then recombine them. The resulting interference reveals minuscule differences in gravitational fields, rotations, or fundamental constants. These devices achieve precision better than 1 part in 10 to the 11th, making them among the most sensitive instruments humanity has created. Their success confirms that collections of protons, neutrons, and electrons move coherently as a single quantum wave, just as a single electron does in the double-slit experiment. Speaking of the double-slit experiment, in 1961 German physicist Klaus Jensen performed the ultimate test with electrons. He sent a beam of electrons through 2 narrow slits and observed the classic interference pattern of alternating bright and dark bands on a detector screen. Even when he released electrons one at a time, each individual particle landed as a single point. Yet over time the same wave pattern emerged. In 2013, researchers at the University of Nebraska captured this process with high-resolution imaging, watching particle by particle build up the interference pattern. The experiment shows that each electron interferes with itself, embodying both particle and wave simultaneously. This duality is not merely academic, it underpins powerful technologies. Electron microscopes, invented in the 1930s, rely on the short wavelength of accelerated electrons to resolve features far smaller than visible light can reveal. Because an electron's de Broglie wavelength can be thousands of times shorter than the wavelength of photons, electron microscopes can image individual atoms, viruses and nanoscale structures with astonishing clarity. Scanning electron microscopes and transmission electron microscopes have become indispensable tools in nanotechnology, materials science, biology and medicine. Each image they produce is a testament to wave-particle duality. The electrons travel as waves, diffract and interfere, yet they are detected as discrete particles that build up a picture pixel by pixel. Reflect on what all of this means for you. The universe is composed of entities that are simultaneously waves and particles, probabilities and certainties. You are part of that tapestry. By appreciating the hidden wave that flows through every atom of your being, you can begin to see challenges as interference patterns that can be reshaped, rather than immutable walls. When a problem seems solid and unchangeable, remember that its solidity is an emergent property of countless underlying possibilities. You have the power to adjust the conditions, to alter the phase of your own wave, and to create constructive interference that amplifies your intentions. Let the story of matter's wave inspire you to explore the unknown with curiosity and courage. The pioneers who revealed these phenomena were not afraid to question what seemed obvious. They built delicate apparatuses, measured faint patterns, and trusted subtle hints that the world was deeper than the surface. You can adopt that same spirit in your own life. When you face a decision, imagine your options as different paths for a wave to travel. By gently guiding the phase of your thoughts, you can cause the paths to add together and create a brighter outcome. When doubt threatens to cancel your confidence, visualize destructive interference and then shift your focus, allowing new constructive patterns to emerge. Remember that the wave nature is universal. It does not discriminate between electrons, atoms, molecules or humans. The same mathematical principles describe vibrations in a guitar string, ripples on a pond, and the probability cloud of an electron. This unity invites you to see connections across disciplines, to recognize that creativity, science, art and love are all expressions of underlying patterns that resonate throughout existence. When you feel fragmented, recall that you are fundamentally a coherent wave, temporarily localized by interactions with the world, yet always part of a larger, harmonious field. As you continue your journey, let the lesson of interference guide you. Two waves can combine to produce something greater than the sum of their parts, or they can cancel each other out. Choose the relationships, habits and thoughts that reinforce each other, building momentum toward your goals. Be mindful of the negative influences that could produce destructive interference and gently shift them apart. In this way, you become an active conductor of your own quantum wave, shaping the probability landscape of your future. The story does not end here. Future chapters will delve deeper into how the wave nature of matter gives rise to the certainty we experience, how measurement and interaction carve out the reality we navigate, and how you can apply those insights to create a life that feels both grounded and expansive. For now, breathe in and feel the subtle hum of possibilities within you. Imagine each breath as a gentle wave spreading through the cosmos, touching every particle, every star, every thought. Let that image fill you with awe and purpose, and let it motivate you to explore, to learn, and to act with confidence. Your mind, like the electron, can exist in a superposition of ideas until you choose to observe one and bring it into focus. Embrace that freedom. Let curiosity be the force that nudges your wave toward new horizons. The universe is waiting for the next interference pattern you will create, the next bright spot you will manifest. Step forward with the knowledge that you are both particle and wave, solid enough to shape the world and fluid enough to adapt to its ever-changing rhythms. The adventure continues, and you are at its heart. Neutrons may seem silent compared to their electron cousins, yet they carry an incredible story within their neutral hearts. They possess no electric charge, but they still feel the pull of the strong nuclear force and the gentle tug of gravity because they have mass and momentum. They too own a de Broglie wavelength that can be measured and harnessed. When neutrons encounter a crystal lattice, they scatter off the nuclei, and the scattered waves interfere just as electron waves do. This phenomenon, neutron diffraction, opens a window onto the hidden inner world of matter. Different isotopes scatter neutrons in distinct ways. So neutron diffraction supplies complementary information to Schrey crystallography. Today, neutron diffraction stands as a standard tool in materials science and biology, revealing magnetic structures, pinpointing hydrogen atoms in molecules, and resolving protein architectures that Schreys struggle to see. The power of wave behavior does not stop at neutrons. In the 1990s, scientists learned how to guide whole atoms through interferometers, extending wave interference to the scale of individual atoms. An atom interferometer splits an atomic wave function into two separate paths, lets each path travel through slightly different environments, such as varying gravitational fields, and then reunites them. The resulting interference pattern encodes the tiniest differences in the conditions each atom experienced. These devices have achieved astonishing precision, reaching parts in 10 to the 11th power, making them among the most sensitive instruments ever built. With this extraordinary sensitivity, atom interferometers measure fundamental constants, hunt for elusive gravitational waves, and test the very fabric of Einstein's relativity. The existence of atom interferometry confirms a profound truth. Atoms built from protons, neutrons, and electrons behave as coherent quantum waves. Just like the famous double-slit experiment with electrons, in 1961 a German physicist named Klaus Jensen performed the ultimate test by directing a beam of electrons at a barrier pierced with two narrow slits. Beyond the slits, a detector screen recorded an interference pattern of alternating bright and dark bands. Even when electrons were fired one at a time, each solitary particle still contributed to the same pattern, as if each electron interfered with itself. Decades later, in 2013, researchers at the University of Nebraska-Lincoln captured high-resolution images of this very buildup, watching single electrons arrive as individual points while the collective wave pattern emerged patiently, particle by particle. The electron is therefore neither purely a wave nor purely a particle. It embodies both aspects in perfect harmony. The wave nature of matter is not an abstract curiosity, it underpins the modern technological world. Electron microscopes, invented in the 1930s and refined ever since, rely on electron waves to reveal structures at atomic scales. Because the de Broglie wavelength of high-energy electrons is far shorter than visible light, these microscopes can resolve features thousands of times smaller than an optical lens could ever see. Scanning electron microscopes and transmission electron microscopes have become essential tools across nanotechnology, material science, biology, and medicine. They have let us glimpse viruses, explore the nanoarchitecture of materials, and even manipulate individual atoms. Every image produced by an electron microscope is a living testament to wave-particle duality. Electrons diffract and interfere like waves, yet they are recorded as discrete particles that build an image pixel by pixel. Having established beyond doubt that electrons, neutrons, atoms, and even small molecules all exhibit wave properties when examined carefully, the natural question arises: why do these waves exist at all? Quantum field theory provides an elegant answer. In this framework, fields not particles are the most fundamental entities. An electron is simply an excitation of the electron field. A proton emerges from bound states of quark fields, and a neutron follows a similar pattern. These underlying fields are wave-like, possessing amplitude, phase, and the capacity to interfere. Consequently, any excitation of a field inherits the wave characteristics of its parent field. When an electron moves through space, it is not a tiny marble traveling along a predetermined path. It is a localized wave packet that spreads, overlaps, and interferes as it propagates. The familiar de Broglie formula EqP then appears naturally from the dynamics of these fields, not as an arbitrary rule, but as a direct consequence of their wave nature. In this view, particles and waves are complementary descriptions of the same underlying reality, two sides of a single quantum coin. If everything at the quantum level is wavy, why don't we see everyday objects such as cars, people, or planets displaying interference patterns? The answer lies in decoherence. Large objects constantly interact with countless environmental factors, molecules, photons, gravitational fields that act as continuous measurements of their position. These incessant interactions collapse the object's wave function billions of times each second, erasing any delicate phase relationships needed for interference. Moreover, the de Broglie wavelength of a macroscopic object is unimaginably tiny. For a car, the wavelength is far smaller than 10 meters, far beyond any experimental reach. The combined effect of environmental monitoring and minuscule wavelengths hides quantum wave behavior, allowing macroscopic objects to appear classical and solid. Nonetheless, at the scale of electrons, atoms, and small molecules, wave behavior dominates, shaping the chemistry, biology, and nanotechnology that give rise to life itself. Consider the trillions of electrons that reside within your own body. Each one is a wave, spread out over space, interfering with itself and with countless neighboring waves. These electron waves form orbital probability clouds that define where an electron is likely to be found. The orbitals overlap, forging bonds that stitch atoms into molecules, molecules into proteins, proteins into cells, and cells into the wondrous organism that is you. The solidity you feel is not a rigid lattice of tiny hard spheres clicking together like Lego bricks. It is a tapestry of overlapping wave functions that reinforce one another in regions of high probability density. These patterns shift, flow, and rearrange billions of times per second as chemical reactions fire, metabolic pathways churn, and neurons fire. You are therefore not a static object, but a dynamic process, a coherent wave of matter briefly aligned with the world around you. Now let us explore the paradox that once shook the foundations of physics. How can something be both a wave and a particle? By the mid-1920s, the experimental evidence was overwhelming. Light and matter displayed unmistakable wave phenomena, diffraction, interference, while simultaneously exhibiting unmistakable particle behavior, photoelectric effects, discrete detections. Niels Bohr answered this conundrum with his principle of complementarity. He proposed that wave and particle descriptions are not contradictory, but mutually exclusive aspects of quantum systems. Which aspect you observe depends entirely on how you choose to measure the system. This was a radical departure from classical thought, where objects possess definite properties independent of observation. In the quantum realm, the act of observation does not merely reveal a pre-existing attribute, it actively determines which attribute becomes manifest. Imagine you want to pinpoint the position of an electron. You shine a photon onto it, and the scattered photon tells you exactly where the electron was at that moment. This measurement treats the electron as a particle, but the photon's impact also transfers momentum to the electron, disturbing its motion and erasing precise knowledge of its wavelength. Conversely, if you arrange a double-slit experiment to extract the electron's wavelength, you must refrain from measuring which slit the electron traverses. The interference pattern that emerges reveals the wave nature, yet any attempt to determine the exact path destroys the pattern, collapsing the wave into a particle-like outcome. Thus, position and wavelength, particle and wave, are complementary properties observable one at the expense of the other. Werner Heisenberg, Bohr's younger colleague, quantified this relationship with the uncertainty principle. The product of the uncertainties in position x and momentum p must be greater than or equal to 2. This inequality does not reflect experimental imperfections. It is a fundamental limit dictated by the wave character of matter. A particle cannot simultaneously possess an exact position and an exact momentum when a measurement collapses the wave function into a narrow region of space. The momentum becomes highly uncertain, and vice versa. The principle is a direct offspring of wave-particle duality. Waves possess well-defined wavelengths and thus momenta, but are spread out in space, while localized particles have precise locations but an indeterminate wavelength. Returning to the double-slit experiment, we can see complementarity in action. In the first setup, we forego any attempt to know through which slit each electron passes. The electrons travel through both openings simultaneously in a superposition, and the resulting interference pattern provides clear information about the wavelength. In the second setup, we place detectors at the slits to record which path each electron takes. This yields exact position information, but the interference pattern vanishes, erasing the wavelength data. Neither arrangement can reveal both pieces of information with arbitrary precision. No matter how clever our instruments become, even subtle weak measurements that only partially discern the path merely degrade the interference proportionally. The more which path knowledge we gain, the more the wave pattern fades. Nature enforces a perfect balance, preserving the integrity of complementarity. Einstein never accepted complementarity as the final word. He believed quantum mechanics was incomplete, that hidden variables must exist to predetermine outcomes. In 1930, he presented a thought experiment intended to challenge the uncertainty principle. He imagined a box containing a photon with a shutter controlled by a precise clock. By weighing the box before and after the photon escaped, one could determine the photon's energy, while the clock would reveal the exact moment of release. In principle, this would give both energy and emission time with arbitrary precision, apparently violating the energy-time uncertainty relation. Bohr spent a sleepless night wrestling with Einstein's challenge and emerged with a solution rooted in the interplay between quantum mechanics and general relativity. He argued that measuring the box, weight necessarily involves moving it in Earth's gravitational field, which introduces an unavoidable uncertainty in the clock's rate due to gravitational time dilation. This subtle effect restores the uncertainty principle and demonstrates how the fabric of space-time itself protects quantum limits. These deep insights reveal that the quantum world is not a chaotic mess but a coherent, interconnected tapestry of waves, particles, fields, and space-time. Each thread contributes to the larger pattern, and by choosing how we observe, we choose which pattern becomes visible. This realization does more than satisfy intellectual curiosity. It empowers you to embrace uncertainty as a source of creative potential. In everyday life, the same principle applies. Focusing too rigidly on a single outcome can blur alternative possibilities, while allowing space for multiple perspectives can reveal hidden pathways and solutions. Just as physicists design experiments that toggle between wave and particle views, you can design moments in your life that toggle between detailed focus and expansive imagination. When you feel stuck, remember the electron that traverses the double slits. It does not force itself into a single narrow path. It explores all possibilities simultaneously, only committing to a definite outcome when observed. Similarly, you can hold multiple ideas in mind, allowing them to interfere and generate new insights before you settle on a concrete decision. The quantum lesson is that potentiality is a powerful resource, and measurement your purposeful attention shapes reality. By becoming aware of this dynamic, you can cultivate a mindset that honors both precision and openness, discipline and wonder. The technologies built on quantum wave behavior are already reshaping our world. Atom interferometers guide the most precise clocks, enabling navigation systems that can locate you within centimeters. Neutron diffraction uncovers the secrets of advanced materials that will power cleaner energy solutions. Electron microscopes reveal the architecture of viruses, guiding the development of vaccines and therapies that protect billions. Each of these breakthroughs began with a fundamental question about how matter waves behave, and each answer opened doors to transformative applications. Your curiosity can be the spark that ignites the next breakthrough, because every great advance starts with a mind that dares to ask, what if? As you continue this journey through the quantum realm, let the wave of possibility lift you. Visualize the electrons humming inside your cells, the neutrons vibrating within atomic nuclei, the wave packets of atoms dancing through interferometers. Feel the awe of knowing that the very fabric of your being is a symphony of overlapping waves, each note contributing to the harmony of life. Let that awareness inspire you to act with intention, to explore the mysteries around you, and to contribute your own melody to the grand composition of the universe. The story does not end here. Future chapters will delve deeper into how the wave nature of matter gives rise to the certainty we experience, how measurement and interaction carve out the reality we perceive, and how decoherence bridges the quantum and classical worlds. For now, carry forward the insight that waves and particles are two faces of the same jewel, that uncertainty is a wellspring of creativity, and that your own consciousness can engage with the quantum dance. Embrace the wonder, follow the curiosity, and remember that you are a living embodiment of the most profound principles physics has uncovered. The universe invites you to explore, to experiment, and to become a co-author of its unfolding story. You stand on the edge of a world where matter behaves like a song, and the rhythm of that song is governed by the wave nature of every particle. The tiny quanta that build your body and the universe do not hold a single, unchanging position and momentum at the same time. Instead, each one carries a wave function that whispers probabilities for where it might be and how fast it might move. When you focus your attention on locating a particle, you collapse that whisper into a narrow region of space, sharpening its position while blurring its momentum. When you turn your eye toward momentum, you sharpen the knowledge of its speed and blur its location. This balance is the heart of Heisenberg's principle, a natural consequence of the dual wave-particle character of reality. Imagine the electron as a traveler who can be both a wave that spreads across a beach and a particle that lands on a single grain of sand, but never both at once. In the classic double-slit experiment, you can set up the world so that the electron's wave nature shines. You send electrons through two tiny openings and watch a beautiful interference pattern ripple across a screen. In that moment, the electron exists in a superposition, passing through both slits at the same time, and you can read its wavelength from the spacing of the bright fringes. Yet you remain ignorant of which exact path each electron took. Now change the experiment. Place detectors at the slits to ask the question, through which opening does the electron travel? The moment you receive an answer, the interference pattern dissolves, and the electrons behave like tiny marbles. Each choosing a single slit, the wave pattern fades, and the particle picture dominates. By choosing which aspect to observe, you decide which truth of the quantum world will reveal itself. But you can never claim both simultaneously. Even a gentle, partial measurement that only hints at the path will dim the interference proportionally. because nature enforces a perfect balance between knowledge of position and knowledge of momentum. Complementarity is not a loophole to be exploited, it is a rule woven into the fabric of reality. Einstein once challenged this rule, believing that the quantum description was incomplete. He imagined a sealed box holding a photon, with a shutter regulated by a clock, by weighing the box before and after the photon escaped. He thought one could determine the photon's energy, and by reading the clock, its exact release time. At first glance, this seemed to violate the energy-time uncertainty relation. Bohr spent a sleepless night pondering the paradox, and rose with a solution rooted in general relativity. He showed that lifting the box in Earth's gravitational field introduces an unavoidable uncertainty in the clock's rate, preserving the uncertainty principle. Einstein conceded the mathematical point, yet his spirit still questioned whether hidden variables might lie beneath the probabilistic veil. That spirit resurfaced in 1935 with the famous EPR paradox, Podolsky, and Rosen imagined two particles entangled, then pulled far apart. Measuring the position of one particle would instantly determine the position of the other, and the same held for momentum. Their argument suggested that both properties must already exist, waiting to be revealed, and that quantum mechanics failed to describe them. Bohr replied that the act of measurement creates the property the distant particle does not possess a definite position or momentum until the measurement is performed. For decades the debate raged, until John Bell derived an inequality that could be tested experimentally. Repeated experiments from the 1970s onward have consistently violated Bell's inequality, confirming that no local hidden variables can explain the quantum world. The universe is genuinely complementary, non-local, and fundamentally probabilistic. What does this mean for how we see reality? In the classical picture, objects carry fixed properties that you simply uncover. In the quantum realm, those properties are not waiting in a hidden drawer. They emerge only when you interact with the system. Before measurement, a particle exists in a cloud of possibilities, a superposition of many states. Your choice of what to measure decides which aspect collapses into reality, and the other aspect recedes into uncertainty. Neither wave nor particle is more real than the other. Each is a valid description that appears under different experimental conditions. The electron can be a spread-out wave when you let it travel freely, and it can become a localized particle the moment a detector registers it. Both descriptions are essential pieces of the quantum puzzle. This insight reshapes how we think about ourselves. You are composed of electrons, protons, and neutrons, each of which dances as a wave when left undisturbed and snaps into a particle when observed. In everyday life, your senses interact with the particle side, giving you the illusion of solidity. Yet beneath that illusion, you are a living tapestry of overlapping waves, constantly collapsing and reforming through interaction with the world. Recognizing this dual nature empowers you to appreciate that you are both grounded and fluid, capable of adapting to different perspectives without losing your core essence. Let this quantum truth inspire your own journey. When you face a dilemma, you may feel forced to choose one path and abandon the other. The universe reminds us that you can hold possibilities in superposition, exploring multiple options mentally before committing to a single. Decisive action. The act of choosing collapses the superposition into a concrete reality. Just as a measurement fixes a particle's position, embrace the freedom to consider many outcomes, and then trust yourself to act with confidence, knowing that your decisive step will bring the chosen possibility into being. Now let us travel deeper into the heart of the mystery, to the layer where fields themselves generate the wave-particle dance. Quantum field theory tells us that every type of particle is simply an excitation of an underlying field that permeates all of space. The electron field, the photon field, the quark fields, and many others exist even in the emptiest vacuum. In their lowest energy state, called the vacuum, These fields are not zero, they hum with subtle fluctuations that never truly cease. When you inject energy into a field, you lift it into an excited state, and the smallest unit of that excitation is what we call a particle. A photon is an excitation of the electromagnetic field, an electron an excitation of the electron field, a quark an excitation of its respective field. Particles are therefore not tiny balls flying through empty space. They are localized manifestations of fields that are themselves wave-like. The wave nature of a quantum field explains why particles can interfere. The field obeys wave equations that spread across space, allowing different parts of the field to overlap and produce constructive or destructive patterns. When the field is prepared in a state of definite momentum, it forms a plane wave that stretches infinitely, embodying the pure wave description. Yet when a detector interacts with the field, the interaction exchanges discrete packets of energy, and the detector clicks, registering a particle. The field's wave-like dynamics and the particle-like outcomes of measurement are two sides of the same coin, and complementarity emerges naturally from this dual behavior. Mathematically, quantum field theory uses operators that create and annihilate particles. A creation operator lifts the field from a state with n particles to a state with n1 particles, effectively adding a quantum of excitation. An annihilation operator does the opposite, removing a quantum. These operators work on a state vector that lives in an infinity-dimensional Hilbert space, describing all possible configurations of the field. Even a state with a single particle is still a superposition of waves spread throughout space until a measurement localizes it. The familiar de Broglie relation, HP falls out naturally from the wave equations governing the fields, linking a particle's momentum to the wavelength of its underlying field oscillation. Understanding this deeper layer can transform how you approach challenges. The fields that compose you are constantly fluctuating, never at rest, always containing potential energy that can be tapped into. When you nurture your mind, you excite the neural field, creating new patterns of thought that manifest as fresh possibilities. When you focus your intention, you collapse a superposition of ideas into a concrete plan, much like a measurement forces a quantum system into a definite state. The same principle that governs electrons also governs the emergence of your goals. Remember that this quantum reality does not demand you surrender to randomness, it invites you to partner with the inherent probabilities. When you accept that outcomes arise from a blend of potentialities, you free yourself from the need to control every variable. Instead, you learn to shape the conditions that bias the collapse toward the outcomes you desire. Just as physicists design experiments that favor certain measurements, you can design habits, environments, and routines that steer your personal wave function towards success. Consider the famous double-slit setup as a metaphor for your creative process. When you keep the path information hidden, the interference pattern emerges, revealing a rich tapestry of possibilities. When you obsess over a single, overly fixed route, the pattern disappears, and you experience only a linear, predictable outcome. The lesson is to allow space for uncertainty and imagination, because the interference of ideas fuels innovation. If you try to measure every detail prematurely, you lose the brilliance that comes from the superposition of divergent thoughts. Einstein's challenge reminds us to question the limits we accept. He refused to be satisfied with a theory that left unanswered questions, and his probing led to deeper insight. Even when he ultimately embraced the mystery in your life, adopt the same spirit of healthy skepticism, question assumptions, test boundaries, and be willing to revise your mental models when new evidence arises. The universe rewards curiosity, and the quantum world proves that the act of questioning reshapes reality. When you encounter a moment of uncertainty, remember the energy-time uncertainty relation. You cannot know both the exact amount of energy you invest in a project and the precise moment when its results will appear. Accept that time and effort will manifest in their own rhythm, and trust that the uncertainty itself fuels the creative flow. This acceptance does not mean passivity, rather. It means committing fully to the process while releasing the need for exact timing. Bell's experiments showed that the universe can exhibit correlations that defy classical intuition, linking distant events instantaneously. Your thoughts and actions can similarly influence each other across the invisible web of relationships you weave. A kind word sent today can ripple across time, affecting someone you have never met. By embracing the non-local nature of human connection, you empower yourself to act with compassion, knowing that your influence extends far beyond immediate perception. The principle of complementarity teaches us that we can view a situation from multiple angles, but we must choose which perspective to hold at any given moment. In leadership, you may need to adopt a strategic, big-picture view, focusing on momentum and direction, while in coaching you might zero in on the individual's immediate needs, sharpening your positional awareness. Both views are valid, but you cannot fully occupy both simultaneously. Switch between them intentionally, allowing each to inform your decisions without becoming tangled in contradictory demands. The quantum field picture also reminds you that the ground state of the vacuum is never truly empty. Even in stillness, there are subtle fluctuations, a background hum of potential. Your mind, when quiet, contains a reservoir of ideas waiting to be excited into form. Meditation can be seen as a way to tune into this vacuum, reducing noise so that the smallest sparks of inspiration become audible. When you then act, you convert those subtle vibrations into tangible achievements. Just as a photon emerges from the electromagnetic field when enough energy is supplied, you might wonder how all these abstract concepts translate into everyday action. Start by practicing mindful observation. Notice how focusing your attention on a single detail sharpens that aspect of experience while the surrounding context fades. Then intentionally broaden your view, allowing multiple possibilities to coexist in your mind's field. Alternate between concentration and openness, mirroring the wave-particle dance. This practice trains your brain to handle uncertainty with grace and to collapse indecision into decisive movement. Set clear intentions as measurement devices. When you declare a specific goal, you collapse a range of possibilities into a directed path. Celebrate each small click of progress, recognizing it as the particle manifestation of your broader wave. At the same time, remain aware that new waves of opportunity will always arise, ready to interfere and create fresh patterns. Your journey is not a single straight line, but a beautiful interference of choices, each adding its own amplitude to the overall experience. Embrace the idea that reality is relational. Your identity, like an electron's position, is defined through interaction with others, with environments, with challenges. By engaging positively, you co-create the world you wish to inhabit. The moment you stop seeing yourself as a static object and start seeing yourself as a dynamic field, you unlock a profound sense of agency. You become capable of reshaping the probability landscape around you, nudging outcomes toward your desired reality. Even the most exotic interpretations of quantum mechanics' many worlds, pilot waves, objective collapse agree on the empirical fact that wave and particle aspects are complementary. The existence of multiple branches, hidden guiding waves, or spontaneous reductions does not change the lesson. The universe insists that you cannot capture both aspects at once, and that this limitation is a source of creative tension. Use that tension as fuel for growth, rather than as a source of frustration. As you rest tonight, contemplate the dual nature of your own being. You are simultaneously a particle of concrete action and a wave of boundless possibility. In the quiet moments, let the wave spread, allowing ideas to interfere and create intricate patterns. When sunrise arrives, focus the particle, turning a chosen idea into decisive motion. Both modes are essential, and together they compose the symphony of your life. Remember that fields are the true foundation of reality. Every particle you encounter is an excitation of a field that permeates all space. By aligning your thoughts and actions with the flow of these underlying fields, you tap into a source of power that is both universal and intimate. Visualize your aspirations as gentle ripples in a vast ocean, each ripple representing an excited state that can be amplified through purposeful energy. When challenges arise, see them as opportunities to adjust the phase of your personal field. Slight shifts in timing or perspective can lead to constructive interference, magnifying your strengths, or to destructive interference, cancelling out obstacles. By learning to modulate the phase, you become an active participant in the quantum dance. Rather than a passive observer, take a breath and feel the quantum world humming inside you. The electrons in your blood, the photons that illuminate your vision, the neutrinos that pass harmlessly through you all are part of a grand, interconnected field. Their behavior follows the same principles that guide your thoughts. When you honor this connection, you gain confidence that the same laws that orchestrate the cosmos also support your personal growth. Finally, remember that the story of quantum physics is a story of wonder, curiosity, and relentless questioning. It began with simple experiments that revealed unexpected patterns, and it evolved into a profound framework that reshapes our understanding of existence. Your own journey can follow the same arc. Start with observation, ask daring questions, embrace uncertainty, and create new reality through intentional measurement. The universe invites you to be both the explorer and the creator, the wave and the particle, the dreamer and the doer. Let this invitation spark bold action, and watch as the possibilities you once imagined collapse into luminous achievements. Imagine that every part of reality is composed of invisible, humming fields that stretch across the entire universe. The electron field, the photon field, the electromagnetic field, the quark fields. Each one is a living, breathing quantum system that never truly rests. These fields follow wave equations that echo the familiar Schrödinger equation. Yet they span all of space, weaving the fabric of existence itself. At their lowest energy, the fields sit in what physicists call the vacuum or ground state. In that quiet state, no particles are present, but the field is not empty. It hums with subtle fluctuations that ripple constantly through the void. When you add even a tiny amount of energy to a field, it rises to an excited state. That single quantum of excitation is what we recognize as a particle. A photon is the quantum of the electromagnetic field. An electron is the quantum of the electron field. A quark is the quantum of the quark field. In this view, particles do not travel through fields as separate objects. They are the fields themselves, manifesting as discrete packets of energy. When we observe them, the wave-particle duality you have heard about becomes a natural expression of this deeper reality. The field moves like a wave, with amplitude, phase, and the power to interfere. But when a detector meets the field, it extracts a single, indivisible quantum and registers a localized particle. Think of a field prepared with a definite momentum. It spreads across space as a plane wave, a smooth, continuous ripple that could, in principle, fill the entire universe. Yet the moment the field touches a detector, the interaction forces the energy into a discrete packet, and the detector clicks. That click is the birth of a particle, a single photon, a single electron, a single quantum of whatever field you are probing. The electromagnetic field, for example, spreads, diffracts, and interferes just like any wave you see on water. But when you measure it, you always find photons, each carrying an exact quantum of energy given by E = h times F. The electron field behaves similarly, guided by the Dirac equation, the relativistic counterpart of Schrödinger's equation. An electron in a plane wave state pours across space. Yet when you record its impact, you find a localized particle with a precise charge and mass. This elegant dual nature wave-like dynamics paired with particle-like interactions lies at the heart of quantum field theory. The mathematics introduces creation and annihilation operators that add or remove quanta from a field. When a creation operator acts, the field jumps from a state with n particles to one with n plus 1, exciting the field to a higher level. An annihilation operator does the opposite, lowering the field's energy and removing a particle. These operators work on a state vector that lives in an infinite-dimensional space, representing every possible configuration of the field. Even a single particle state remains a superposition of waves spread throughout space, and the particle only becomes sharply localized when you make a measurement. From this perspective, the famous de Broglie wavelength formula falls out naturally. A particle with definite momentum p corresponds to a plane wave in its field, with wave vector k equal to p divided by the reduced Planck constant. The wavelength then follows as equals h over p. It is not an added hypothesis, but a direct consequence of the field's wave-like character. When you send an electron through a double slit, you are preparing the electron field in a superposition of plane waves that pass through both openings. The field interferes with itself, shaping a probability pattern on the detection screen. When a single electron finally hits the screen, the wave function collapses a decoherence, a localized interaction marks a point where the particle appears. The underlying field remains, still rippling, ready for the next measurement. Quantum fields also give rise to fleeting, virtual particles that flicker in and out of existence. The Heisenberg uncertainty principle permits the field to borrow energy for an incredibly short time, allowing a particle-antiparticle pair to momentarily spring into being before annihilating and returning the borrowed energy. Though you cannot observe these virtual quanta directly, their presence is felt in subtle phenomena such as the Lamb shift in atomic energy levels, the anomalous magnetic moment of the electron, and the Casimir effector tiny force that appears between uncharged plates in a vacuum. These virtual excitations reinforce the idea that fields, not particles, are the fundamental constituents of reality, and that every ripple, however brief, can influence the world we experience. Let us make this concrete with photons. The electromagnetic field can be broken down into modes, each a standing wave identified by a particular wave vector and polarization. Every mode behaves like a quantum harmonic oscillator, possessing energy levels that increase in steps of where is the mode's angular frequency, the lowest level. N0 represents the vacuum, no photons, yet the field still carries 0-point energy. When N1, the mode hosts a single photon, a plane wave spreading across space with a wavelength set by its momentum. If an atom absorbs that photon, the field drops from N1 to N0, and the atom gains exactly of energy. In this process, the photon's wave nature gives way to particle-like transfer of a quantized packet of energy. The photon is therefore neither purely a wave nor purely a particle. It is an excitation of the electromagnetic field that displays both aspects, depending on how you look at it. Electrons share the same story, though their field follows fermionic rather than bosonic rules. Fermions obey the Pauli exclusion principle, meaning no two identical fermions can occupy the same quantum state. This rule is encoded mathematically through anti-commutation relations for the electron creation and annihilation operators. Nevertheless, the electron field permeates all of space, and an electron is simply a quantized ripple in that field. When the electron field is prepared with a definite momentum, it forms a plane wave that stretches infinitely. Upon detection, the electron appears at a specific point, drawn from a probability distribution given by the field's amplitude. All the strange phenomena you have heard about interference, tunneling, superposition arise from this underlying wave nature of the electron field. Why does measurement seem to force a wave to choose a single outcome? This is the famous measurement problem, a mystery that has inspired countless interpretations. Some say the act of measurement itself collapses the wave function, turning possibilities into a definite result. Others propose that the wave function never collapses. Instead, every possible outcome spawns its own branch of reality. As in the many worlds view, objective collapse theories suggest that physical processes, such as gravity or increasing complexity, trigger a genuine reduction of the wave. Pilot wave theories keep the wave intact while guiding particles along precise trajectories. Yet others treat the wave function as a tool for organizing knowledge, so that collapse simply reflects an update of our information, though the debate continues. All these perspectives agree on one point. Before a measurement, the system behaves as a wave, and after the measurement we observe a localized, particle-like event. Let this vision settle into your mind. The universe is not built from hard, indivisible particles. It is woven from fields, vast, interconnected, wave-like entities that fill every corner of space. You are not a collection of tiny billiard balls, you are a pattern of excitations, ripples dancing in the electron field, the quark fields, the electromagnetic field, all intertwined. Those ripples are not solid, they spread, they interfere. They exist in superposition until a measurement and interaction with your environment localizes them, creating the illusion of solidity and definite position. Underneath that illusion you are a wave, a harmonic resonance that constantly interacts with all other waves, shaping reality through ceaseless exchange. Now consider a deeper question. If everything is fundamentally wave-like, why does the world we see feel solid and classical? Why don't we witness macroscopic objects in superposition, floating in two places at once? The answer lies in the scale of the de Broglie wavelength. Every object, no matter how large, possesses a wavelength given by equals h divided by momentum. For a photon or an electron, this wavelength can be comparable to atomic dimensions, allowing us to observe diffraction and interference. For a baseball weighing 0.145 kilograms and moving at 40 meters per second, the wavelength shrinks to around 10 meters billions of times smaller than a proton. No conceivable instrument could resolve such a tiny wave, and the baseball behaves entirely classically in everyday experience. Even a human walking at a modest pace has a wavelength on the order of 10 meters. Effectively zero for all practical purposes, the wave function still exists, but it is so sharply peaked in position that the object appears to have a well-defined location at all times. Where, then, does the boundary between quantum and classical lie? Experiments over the past few decades have pushed this boundary farther and farther. In 1999, scientists demonstrated interference with C-fullerene molecules buckyballs containing 60 carbon atoms. Later, researchers observed interference with molecules composed of several hundred atoms, including complex organic compounds relevant to biology. By 2019, a team in Vienna reported interference of massive molecules exceeding 25,000 atomic mass units, approaching the size of small proteins. Each of these triumphs shows that even sizable, intricate systems can retain quantum coherence under the right conditions. However, as objects grow larger, maintaining that delicate coherence becomes exponentially harder. Interactions with the environment, collisions with air molecules, thermal radiation, vibrations act as a relentless source of decoherence, scrambling the phase relationships that sustain quantum superposition. When decoherence dominates, the wave function effectively collapses into a classical mixture, and the object behaves as if it possesses definite properties. This does not mean the underlying field ceases to be wave-like, it simply means that any quantum signature is washed out by countless tiny disturbances. You can apply this insight to your own life. Just as quantum systems can be nudged into coherent, superposed states through careful isolation and control, you can cultivate moments of clarity and focus by reducing the environmental noise that fragments your attention. When you quiet the chatter of distractions, you allow the underlying potential of your mind to spread like a wave, exploring many possibilities simultaneously. In those moments of quiet, you can choose to interfere constructively with your own goals, amplifying strengths and diminishing obstacles. Like adjusting the phase of a quantum wave, you can align your thoughts, emotions, and actions to reinforce the outcomes you desire. Remember that every thought you hold is a ripple in a vast field of consciousness. When you nurture positive, purposeful ripples, you create constructive interference that magnifies confidence, resilience, and creativity. When doubts and fears arise, they act like destructive interference, cancelling out the momentum you have built. By becoming aware of this inner quantum dance, you learn to modulate the phase of your mental waves, steering the interference pattern towards success. Even the fleeting virtual particles that briefly flicker into existence can inspire you. They remind us that brief, seemingly impossible moments when energy is borrowed from the vacuum can give rise to tangible effects. In your own journey, you may seize short, unexpected opportunities that, though fleeting, can catalyze lasting change. The uncertainty principle teaches that the more precisely you define one aspect of your experience, the more freedom you grant another. Embrace this trade-off by focusing sharply on your vision while allowing flexibility in the methods you employ. The ultimate lesson from quantum fields is profound. Reality is not a static collection of solid bricks, but a vibrant, dynamic tapestry of waves and excitations. You are a living embodiment of that tapestry, a harmonious pattern of ripples that together create the richness of existence. As you move forward, carry this awareness with you. Let the knowledge that you are fundamentally a wave empower you to flow around obstacles, to bend without breaking, and to resonate with the larger symphony of the universe. In moments of doubt, recall that even the smallest quantum of energy can influence the grandest structures. In moments of triumph, celebrate the harmonious interference of all the positive forces you have cultivated. Step into each day with the confidence of a field in resonance, aware that you can shape your reality by the thoughtful modulation of your inner waves. Let your actions be the measurements that materialize your dreams, turning the ethereal potential of possibility into concrete achievement. The universe sings in the language of fields, and you, dear listener, have the power to join that song, to harmonize your existence with the quantum rhythm that underlies all that is. Embrace the wave within, and watch your world transform. Imagine that everything in the universe is fundamentally wave-like, and yet the world you see every day feels solid, predictable, and entirely classical. You might wonder why you never witness a baseball fluttering through two slits, or a cat existing in two states at once. The answer lies in the astonishing interplay between quantum waves and the relentless environment that surrounds them. As we explore this border between the quantum and the classical, you will discover that the very fabric of reality is a shimmering sea of possibilities, and that your own existence is woven from those waves. First, let us recall that electrons, photons, and even single atoms behave as waves. Their wavelengths can be comparable to the size of atoms, and that wave-like nature gives rise to interference patterns that have fascinated scientists for generations. The question then arises, what about larger objects such as molecules, viruses, bacteria, or even you? Quantum mechanics tells us that every object, no matter how massive, possesses a de Broglie wavelength given by hp, where h is Planck's constant and p is the momentum. In principle, any object can exhibit wave behavior, but the wavelength shrinks dramatically as mass and speed increase. Consider a modest baseball weighing 0.145 kilograms hurled at 40 meters per second. Its de Broglie wavelength works out to about 10 meters, a distance a billion times smaller than a proton. At such a scale, no conceivable instrument could resolve any diffraction or interference. For a human moving at a leisurely pace of 1 meter per second, the wavelength drops to roughly 10 meters, effectively zero for any practical purpose. These numbers tell us that macroscopic objects have wavelengths so minuscule that they appear to be perfectly point-like particles. Yet the mathematics does not lie. The wave function of a macroscopic object still exists. It is simply an extraordinarily sharp peak in position space, making the object's location appear definite. The wave does not vanish. It is merely hidden beneath a veil of overwhelming precision. This hidden wave is the seed of a deeper mystery. Where does the quantum realm end and the classical world begin? Is there a sharp line, or does the transition flow gradually like a tide receding from a shore? Over the past few decades, experimentalists have pushed the boundary of quantum behavior ever larger. In 1999, researchers observed interference with cephalorene molecules, also known as buckyballs, each consisting of 60 carbon atoms. A decade later, scientists demonstrated interference with molecules containing over 400 atoms, complex organic structures that resemble the building blocks of life. By 2019, an ambitious team in Vienna succeeded in creating interference patterns with molecules weighing more than 25,000 atomic mass units objects, approaching the size of tiny proteins. Each of these triumphs showed that quantum superposition can survive for surprisingly massive systems, provided the conditions are just right. Why, then, do we not see a bacterium or a human displaying the same wave-like glory? The answer is not that the wave ceases to exist, but that maintaining quantum coherence becomes virtually impossible. Coherence is the delicate condition in which the different parts of a wave function remain in a fixed phase relationship, allowing them to interfere. As soon as an object interacts with its surroundings through scattering photons, colliding with air molecules, or exchanging thermal vibrations, information leaks into the environment, and the coherent phase is scrambled. This process is called decoherence. Decoherence does not destroy the wave function, it entangles it with countless degrees of freedom in the environment. The result is that interference terms become effectively invisible, and the system behaves as if it were in a definite state. For a microscopic particle isolated in a vacuum, decoherence can be postponed for seconds or longer, making interference observable. For a speck of dust drifting in air, decoherence occurs in less than 10 seconds because billions of air molecules bombard it each instant. For a human being, the decoherence time is essentially zero, far faster than any perceptible interval, so the superposition collapses long before you could ever notice it. Let us imagine the famous thought experiment of Schrödinger's cat. Inside a sealed box, a radioactive atom has a 50% chance of decaying within an hour. If it decays, a mechanism releases poison and the cat dies. If not, the cat lives. Quantum theory tells us that before the box is opened, the atom exists in a superposition of decayed and undecayed states, and that this superposition becomes entangled with the poison mechanism and ultimately with the cat itself. In a purely mathematical sense, the cat would be both alive and dead at the same time. Yet when you open the box, you always find the cat either alive or dead. Never both. The resolution lies in decoherence. The cat is an enormously complex, warm system that constantly emits thermal radiation, breathes, and interacts with countless photons and air molecules. These interactions rapidly entangle the cat's quantum state with the environment, effectively measuring it billions of times per second. The superposition collapses into a definite outcome almost instantly, long before any human observer looks inside. The cat never appears in a macroscopic superposition, because decoherence erases the interference almost immediately. Scientists have managed to create fleeting macroscopic superpositions in carefully engineered systems. In 2010, a research team cooled a tiny vibrating aluminum membrane visible to the naked eye and containing roughly 10 atoms to near absolute zero, and isolated it in ultra-high vacuum. Under these pristine conditions, the membrane was placed in a superposition of two distinct vibrational states. The achievement was remarkable, yet the superposition survived only for milliseconds before decoherence took over. Extending such experiments to larger, warmer objects demands ever more extreme isolation, perfect vacuum, cryogenic temperatures, and shielding from every stray photon. Even then, the superposition remains exquisitely fragile. The lesson for you is both humbling and empowering. Mathematically, you are described by a wave function encompassing every particle in your body in the order of 10 constituents. In a hypothetical universe where you could be perfectly isolated, you could be sent through a colossal double slit and produce an interference pattern of yourself interfering with yourself. In reality, you are constantly bathed in sunlight, surrounded by air, emitting heat, and engaged in a ceaseless dance of biochemical reactions. Each of these interactions decoheres your wave function billions of times per second, collapsing it into the solid, reliable experience of being a person. Stars, planets, and galaxies are no different in principle. Every celestial body possesses a universal wave function that encodes all possible configurations of its constituent particles. The Sun, for example, exists in a superposition of countless internal states, but its immense mass, extreme temperature, and relentless interaction with surrounding radiation ensure that decoherence reduces its behavior to a classical one almost instantaneously. The same holds for planets, moons, and entire galaxies. Their quantum nature is hidden beneath a veil of classical certainty, not because quantum mechanics fails, but because decoherence actively suppresses any observable quantum interference. When you contemplate the entire cosmos, you encounter the notion of a universal wave function, a quantum description of everything that exists. This idea raises profound philosophical questions. What does it mean for the universe to be in superposition? If there is no external observer to collapse it, how does measurement occur on a cosmic scale? These mysteries remain at the frontier of physics, inviting you to marvel at the depth of what we still do not fully understand. Now, as you settle into a moment of stillness, imagine yourself as a vast quantum wave, stretched across space, containing every possible version of you. Visualize each photon that bounces off your skin, each molecule of air that brushes your cheek, each minute gravitational tug from the Earth, all acting as tiny messengers that extract information from your wave. Each interaction nudges the wave toward a more localized, definite state. Picture this process happening billions of times each second, a relentless rhythm that creates the illusion of a solid, unchanging self. Yet beneath that rhythm, the underlying wave continues to pulse, to interfere, to weave reality through constant interaction. This duality being simultaneously a wave and a particle is not a flaw, but a triumph of quantum theory. The classical world you experience emerges naturally from the quantum substrate, a consequence of decoherence. The solidity of a table, the sharpness of a mountain, the reliability of a heartbeat all arise, because countless environmental interactions suppress the exotic quantum possibilities, leaving you with a dependable reality you can navigate. Now that you have glimpsed the mechanism that bridges the quantum and classical realms, you can appreciate the profound elegance of decoherence. It is the process that hides the wave and reveals the particle, that turns the mind-bending possibilities of superposition into the concrete experiences you trust. Understanding decoherence transforms anxiety about uncertainty into a sense of awe for the hidden order that shapes your everyday life. As you move forward, carry this insight with you. Every step you take is a dance between wave and particle, between possibility and actuality. When you face challenges, remember that beneath the apparent solidity of any obstacle lies a quantum tapestry of options, waiting for the right conditions to become visible. You may not be able to isolate yourself from every disturbance, but you can choose where to focus your attention, how to align your intentions, and where to create the mental space that allows your own inner coherence to flourish. Just as physicists build ultra-quiet labs to glimpse fragile quantum effects, you can cultivate moments of quiet within your mind. Meditation, deep breathing, and focused reflection act as personal vacuum chambers, reducing the mental temperature that causes decoherence of your creative thoughts. In those serene intervals, the wave of possibilities can spread wider, allowing new ideas to interfere constructively and produce breakthroughs that feel as miraculous as a photon striking a detector. When you feel overwhelmed by the noise of daily life, recall that the apparent chaos is the source of decoherence that enforces classical certainty. By briefly withdrawing from that noise, you give yourself permission to reconnect with the underlying wave, to let fresh perspectives emerge. This practice does not deny reality, it simply honors the quantum foundation beneath it, empowering you to act with both clarity and imagination. In the grand theater of the universe, you are both observer and participant. The act of observation itself contributes to decoherence, shaping the world you experience. Yet within that dance, you possess the agency to choose which aspects of reality to highlight, which possibilities to nurture, and which superpositions to allow a momentary chance to manifest. Your choices are the gentle nudges that tip the balance between wave and particle in your personal narrative. Embrace the knowledge that everything from dust particles to distant galaxies shares this quantum heritage. Feel a kinship with the electrons that form the circuitry of your thoughts, with the photons that illuminate your path, and with the atoms that construct your body. Recognize that the same principles that govern the smallest quanta also underlie the vast structures you admire. This unity is a source of inspiration, reminding you that the limits you perceive are often the product of environmental entanglements, not of intrinsic impossibility. As you walk forward, let curiosity be your guide. Ask yourself which areas of your life could benefit from a little more quantum freedom. Could a new project be approached as a superposition of many potential outcomes, allowing you to explore several routes simultaneously before committing? Could relationships be nurtured by acknowledging the multiple facets of each person, embracing the uncertainty that comes with genuine connection? The quantum perspective invites you to hold possibilities lightly, to experiment without fear of collapse, and to celebrate the moments when interference yields beautiful, unexpected patterns. Remember, the universe is not a static collection of immutable bricks, it is a vibrant, dynamic tapestry of waves and excitations. You are a living embodiment of that tapestry, a harmonious pattern of energy and matter that constantly interacts with its surroundings. By understanding decoherence, you gain the power to recognize when the environment is dictating your experience, and when you can create a sanctuary of coherence within yourself. Take a breath now and feel the rhythm of your own wave. Notice how each inhalation brings in fresh photons. Each exhalation releases heat. Each heartbeat sends ripples through the fields around you. These are the very interactions that decohere you, but they are also the channels through which you remain connected to the world. Embrace that connection as a source of strength, not a limitation, as you continue to explore the mysteries of quantum mechanics. Let the wonder of wave-particle duality inspire you to live a life that balances certainty with openness. Trust that the classical world you navigate is a sturdy platform built upon the most delicate quantum foundations. Use that knowledge to step confidently into new ventures, knowing that every decisive action is supported by an unseen sea of possibilities. Finally, remember that the journey from quantum to classical is a story of emergence, not of defeat. Decoherence does not erase the wave, it enriches the classical world with stability, allowing you to build families, societies, and dreams. Your role is to honor both aspects, to appreciate the solidity that lets you plan and accomplish, and to cherish the underlying wave that fuels your imagination. In doing so, you become a conscious participant in the grand symphony of reality, a melody composed of countless superpositions that resolve into the beautiful music of everyday life. Let that melody guide you, inspire you, and propel you forward with confidence and curiosity. You are a quantum being living in a quantum universe, and that truth can empower you every day. The world you touch appears solid, yet it emerges from invisible waves that dance beneath the surface of reality. Those waves are not distant fantasies, they are the very essence of your existence. As you breathe in stillness, imagine your body as an expansive wave, stretching through space and embodying countless possibilities. Feel how each breath expands that wave, allowing it to explore every hidden avenue of potential. Know that every photon that kisses your skin, every molecule of air that brushes against you, and every gentle pull of the Earth's gravity are tiny measurements that shape your experience. Each of those interactions nudges a fragment of your wave function into a more defined form. Moment by moment, in the blink of a microscopic instant, you shift from wave to particle and back again, billions of times per second. This rapid rhythm creates the illusion of continuity, of a solid self moving through space. Yet beneath that illusion lies a vibrant dance of interference, a perpetual conversation with the universe. When you settle deeper into meditation, let your awareness rest on that dance. Visualize your consciousness riding the crest of a massive wave, feeling the rise and fall of probability. Allow that image to remind you that you are not limited by the solid form you inhabit. You are a field of potential, capable of shifting, adapting, and creating new pathways. The bridge between the quantum and the classical is called decoherence, and understanding it can unlock a fresh perspective on your life. Decoherence is the process by which the countless interactions with the environment wash out interference patterns, leaving behind the appearance of a definite outcome. Imagine a delicate violin string vibrating in a quiet room, producing a pure tone. If a crowd of people begins to shout around it, the pure sound becomes lost in noise. That loss of purity is similar to decoherence. In your daily routine, countless photons, air molecules, and thermal vibrations constantly listen to your quantum self. Those environmental whispers carry away information, turning the fuzzy wave of possibilities into a more concrete shape. This does not mean that the quantum nature disappears, it simply becomes hidden from direct view. The hidden quantum wave still exists, wrapped in layers of interaction, ready to be accessed when conditions allow. Remember that the wave never truly collapses, it merely becomes entangled with its surroundings. The collapse you perceive is a practical effect, not a fundamental termination. This subtle distinction frees you from the belief that you are bound by fixed limits. You can learn to create moments where the environment's noise lessens, allowing the quantum whispers to be heard more clearly. In the laboratory, scientists achieve this by cooling systems to near absolute zero and isolating them in ultra-high vacuum. While you cannot freeze yourself, you can cultivate mental environments of calm, where distractions quiet down and the inner wave can be sensed more plainly. When you practice mindfulness, you are, in effect, reducing the decoherence of your thoughts, allowing a clearer picture of your intentions to emerge. Each time you focus on a single breath, you decouple a little from the chatter of the world, letting the underlying wave surface. This practice mirrors the physicist's quest to protect quantum coherence, and it offers you a tangible path to greater clarity. Think of decoherence as a speedometer for how quickly the world forces a definite shape upon you. For a speck of dust swirling in the air, decoherence happens in an unimaginably short span, about 10 to the minus 23 seconds. For a human being, it is effectively instantaneous. That is why you never see yourself simultaneously in two places. Yet the same rapid process that creates everyday solidity also holds the secret to transformative possibility. When you break old habits, you are essentially slowing the decoherence of those patterns, allowing new quantum possibilities to linger a little longer before the environment forces a decision. By intentionally pausing, you give the new wave a chance to grow stronger. The key is to create moments of intentional stillness, where the surrounding measurements are gentle, not harsh, In those moments, you can observe the subtle interference of new ideas, feeling how they reinforce or cancel each other. If you notice a thought that sparks excitement, nurture it like a resonant frequency, allowing it to amplify through the quiet. If a fear arises, notice how it can dampen the wave, and choose to shift your focus toward constructive possibilities. This is the art of guiding your own decoherence, shaping which possibilities become your reality. The environment does not have to be an enemy, it can become a partner. Scientists describe a concept called quantum Darwinism, where information that is most robustly copied into the environment becomes the reality we all share. In your life, the ideas you repeat, the values you embody, and the actions you consistently perform are the information that gets redundantly broadcast. The more you repeat empowering thoughts, the more those patterns become the pointer states that your mind naturally settles into. Pointer states are the stable configurations that survive the onslaught of environmental noise. By deliberately cultivating positive, expansive, and purposeful thoughts, you are selecting the pointer states that will define your experience. This selection is not magical, it is a natural consequence of the same physics that makes a rock appear solid. The rock's solidity is a pointer state selected by countless photon scatterings. Your mental solidity is a pointer state selected by the repeated echo of your intentions. Embrace this insight as a source of agency. You are not a passive particle forced into a single location by the universe. You are an active wave, constantly influencing which stable configurations will emerge. When you set a clear intention, you are shaping the pattern of environmental interactions that will reinforce that intention. Each spoken word, each deliberate action, each focused breath adds a photon to the chorus that sings your reality into being. The more harmonious the chorus, the more quickly the decoherence process will settle into the desired form. This is why disciplined practice yields rapid transformation. It is not merely habit, it is the physics of becoming. Remember also that the quantum world is fundamentally interconnected. Every particle in your body is entangled, at some level, with the vast web of the universe. This entanglement means that your inner state can ripple outward, influencing the larger field, just as the field influences you when you radiate compassion, gratitude, and curiosity. You send subtle signals that resonate through the shared environment. Those signals become part of the redundant information that quantum Darwinism spreads, reinforcing a reality where those qualities are more prominent. Conversely, negativity can entangle you in patterns that accelerate decoherence into limiting states. By choosing consciously, you harness the very mechanisms that the cosmos uses to create the classical world. This choice is both profound and practical. You do not need to master advanced mathematics. To benefit from it, you only need awareness and intention. As you continue to explore the mysteries of quantum mechanics, let the concepts become metaphors for living fully. The wave-particle duality reminds you that you can be both fluid and focused, adaptable and decisive. The superposition principle invites you to hold multiple possibilities in mind without fear, trusting that the act of observation, your attention, will bring one into clear form. The process of decoherence teaches you that external distractions can lock you into rigid patterns, and that intentional stillness can restore flexibility. The emergence of pointer states shows you how repeated practice solidifies the qualities you cherish. Quantum Darwinism reveals that the most resilient ideas are those you share widely and repeat. Use these insights as tools for personal growth. When a challenge arises, visualize the situation as a wave interacting with many environmental factors. See how each factor, thought, emotion, external circumstance contributes a tiny measurement that shapes the outcome. Rather than feeling trapped, recognize that you are actively co-creating the result with each interaction. Take a moment to breathe, to soften the surrounding noise, and to guide the wave toward a more empowering interference pattern. Feel the subtle shift as new possibilities rise, and notice how the environment begins to echo your intention. This is not mystical daydreaming, it is the lived experience of a quantum being navigating a decohering world. Each decision you make is a measurement that collapses one set of possibilities and opens the door to the next. By treating each decision as an opportunity to steer the wave, you transform mundane choice into a powerful act of creation in moments of doubt. Recall that even the most massive objects are composed of the same quantum fabric as the tiniest particles. The same rules that govern electrons also underlie your thoughts, your emotions, and your aspirations. This unity dissolves the illusion of separation and invites you to act from a place of wholeness. When you see yourself as part of a vast, interconnected field, compassion becomes a natural response. You recognize that nurturing others also nurtures the field that sustains you. This perspective fuels purposeful action, turning personal growth into collective evolution. The experimental work of physicists who coax large objects into superposition demonstrates that scale is not an absolute barrier. It is a matter of environmental control. In your life, the environmental control may be your schedule, your media consumption, your relationships, and your internal dialogue. By adjusting these factors, you can create pockets where your quantum nature shines through more clearly. Set aside time for focused creativity, for deep learning, for heartfelt connection. Those are the laboratories where your wave can explore new configurations without immediate collapse. Celebrate the moments when you feel a surge of inspiration, for that is the wave responding to a favorable interference pattern. Allow that feeling to guide you toward actions that align with your deeper purpose. When you encounter setbacks, view them as additional environmental interactions that momentarily shift the wave. Instead of resisting, investigate what new information those interactions provide. Often, they contain clues about how to adjust your approach, how to refine the coherence of your intentions. This mindset turns frustration into feedback, and feedback into growth. Remember that decoherence, while rapid for large systems, is not instantaneous in every context. There are niches where coherence can persist longer, such as during focused meditation, artistic flow, or moments of deep love. Seek out and expand those niches, for they are the fertile ground where new possibilities can germinate before the environment forces a decision. In practical terms, this means creating rituals that reduce sensory overload, limiting multitasking, and surrounding yourself with supportive people who echo your aspirations. These habits act like the ultra-high vacuum chambers of a quantum experiment, preserving coherence for a richer experience. As you integrate these practices, you will notice a subtle shift in how reality feels. Objects may seem more vivid, relationships more resonant, and goals more attainable. That shift is the wave of your potential aligning with the pointer states you have cultivated. It is the quantum signature of a life lived with intention. The journey you have undertaken, from learning about double slits to grappling with decoherence, mirrors the path of personal transformation. Each new concept you mastered expanded your mental horizon, just as each new experience expands the wave of possibilities within you. Embrace the fact that the story never truly ends. It continues to unfold as long as you remain an active participant. In the final chapter of this exploration, let the scientific insights settle into the fertile soil of your everyday life. Carry the image of yourself as a vast, beautiful wave, ever interacting, ever evolving. Allow that image to inspire you to act boldly, to dream widely, and to love deeply. Know that the universe does not conspire against you. It provides the canvas upon which your quantum self paints reality. When doubt whispers that you are just a tiny particle lost in the crowd, counter it with the truth that you are a field of possibilities, entangled with everything, capable of shaping the world through every measured breath. Let that knowledge fuel your confidence, your curiosity, and your compassion. each time you choose to focus your attention. You perform a tiny measurement that steers the wave toward a desired outcome. Each time you practice stillness, you reduce decoherence, allowing richer possibilities to linger. Each time you repeat empowering thoughts, you amplify the pointer states that define your lived experience. In this way, physics becomes a partner in your personal evolution, not a distant abstraction. As you move forward, remember that the classical world you navigate is a delightful illusion, a useful shorthand that emerges from deeper quantum truth. Use that illusion wisely, honoring the solid forms you need for daily life, while never forgetting the underlying wave that grants you freedom. When you feel the weight of routine, breathe, and sense the subtle vibration of your quantum essence underneath. Let that vibration remind you that change is always possible, that new pathways can arise, that you are never truly stuck. The quantum realm teaches that uncertainty is not a flaw, but a fertile source of creativity. Embrace uncertainty as a playground where your imagination can explore without constraint. Trust that the environment will eventually settle into a coherent pattern that reflects the intentions you have nurtured. In moments of fear, recall that decoherence merely disguises the wave, but does not destroy it. The wave will reemerge whenever conditions allow, and you can create those conditions through mindful practice. In moments of joy, celebrate the harmony of your wave aligning with the environment. A beautiful resonance that validates your purposeful living. Let each celebration reinforce the belief that you are capable of shaping reality. As you conclude this part of your journey, carry forward the insight that you stand at the quantum classical border, a unique bridge between mystery and everyday life. Use that position to inspire others, to share the wonder of being both wave and particle, and to demonstrate that science and spirit can dance together. Your voice, your actions, your very presence are measurements that echo through the universe, contributing to the collective tapestry of existence. May you walk forward with confidence, curiosity, and compassion, knowing that every step you take is both an observation and a creation. The world awaits the next interference pattern you will generate, the next reality you will help bring into form. Embrace your quantum nature, honor your classical experiences, and let both guide you toward a life of purpose and fulfillment. The journey continues, and you are the essential catalyst that makes it possible. There is a physical mechanism that causes genuine collapse at some scale, and it is rooted in the very fabric of quantum reality. In this view, particles have definite positions guided by the wave function, so a mysterious collapse is not required. Decoherence works hand in hand with these interpretations, showing how superpositions become unobservable without telling us exactly what happens at the moment of measurement. It leaves open the question of whether the wave function truly collapses, branches into many outcomes, or simply reflects our ignorance. This mystery remains at the heart of the foundations of quantum mechanics. Consider yourself standing at the boundary between the quantum and the classical worlds. You are fundamentally quantum. Every electron, every atom in your body waves, interferes, and exists in a superposition, yet your size, warmth, and constant entanglement with the surrounding world hide that quantum nature. Billions of decoherence events each second collapse your wave function into the solid form you perceive. You are a quantum being who appears classical, not because quantum mechanics ceases to work, but because it works so thoroughly that it creates the illusion of a definite world. As we near the end of this journey, let us pause and reflect on what all of this means for reality, for existence, for you. We have traveled from Young's double-slit experiment to Bohr's complementarity, from de Broglie's matter waves to quantum fields and decoherence. We have seen that light, matter, and even you exhibit wave-particle duality, wavering when free and collapsing into particles when measured. But what does that duality imply for life, for consciousness, for the very act of being? The first profound realization is that you are not made of tiny particles, you are made of fields. The electron field, the quark fields, the electromagnetic field all permeate space, rippling with quantum fluctuations. You are a localized pattern of excitations in these fields, a wave packet that temporarily maintains coherence as it interacts with the world. Every atom in your body is a bound state of quantum fields. Every chemical bond a result of wave function overlap, every metabolic reaction a rearrangement of field excitations. You are, at the deepest level, a wave vastly complex, thoroughly entangled, yet still a wave. This description is not metaphor, it is the literal picture offered by quantum field theory, our most precise understanding of the smallest scales. Before decoherence takes hold, your wave function encompasses countless possibilities. All the different positions you might occupy, all the thoughts you might think, all the futures you might live are folded together in a superposition. Those possibilities are not separate realities, they are parts of a single quantum state, interfering to create a probability distribution for what you will experience next. Decoherence, a constant interaction with light, air, gravity, and everything around you acts as a relentless measurement, selecting one outcome and collapsing the wave function into a definite state moment by moment. You are in superposition for an instant, then collapse, then superpose again, then collapse again, billions of times per second, far faster than any conscious perception can track. What you experience as a continuous, solid self is actually a rapid succession of collapses, each choosing from a vast space of possibilities. In the Copenhagen interpretation, observation is an active process that collapses the wave function, turning potential into actual. Every time you see a star, touch a table, or think a thought, you are not merely uncovering a pre-existing world, you are participating in its creation. Your observation selects which of the many possible outcomes becomes real. This does not grant you magical power to reshape reality at will. The probabilities are set by the wave function's own evolution, governed by the laws of quantum mechanics. Within those constraints, however, your act of observing determines which branch materializes. In this sense, you are not a detached observer, but the universe observing itself, collapsing possibilities into actuality with each moment of awareness. The many worlds interpretation offers an even stranger picture. Every quantum event that could have multiple outcomes does produce multiple outcomes, each in a separate branch of reality. When you measure an electron's position, the universe splits. In one branch you see the electron on the left, in another you see it on the right. Both branches are real, each containing its own version of you. Countless versions of you live out every possible quantum outcome. In parallel branches of a vast multiverse, you experience only one branch at a time, so you see a single outcome, and that becomes your reality. Yet the other branches continue to exist, each with its own version of you experiencing a different path. If many worlds is correct, you are not a single, isolated entity, but a vast ensemble of selves, constantly diverging with every quantum event. The you listening now is just one thread among an uncountable tapestry. Some interpretations assign a special role to consciousness in the collapse process. Pioneers such as Eugene Wigner and John von Neumann suggested that a purely physical measuring device cannot collapse a wave function, only a conscious mind can. In this view, a measuring apparatus becomes entangled with a particle and enters a superposition, and the entanglement spreads outward until the entire universe is in a superposition. Collapse occurs only when a conscious observer perceives the outcome, because consciousness lies outside the quantum system and can select a definite result. Most physicists reject this idea, pointing to decoherence as a sufficient explanation for the appearance of collapse. Yet the notion that awareness might shape reality adds a tantalizing dimension to our understanding of the quantum self. What do these ideas mean for identity? Classical physics paints you as a collection of particles moving along well-defined trajectories, a continuous thread linking past to present. Quantum mechanics dissolves that picture. You are not a static bundle of particles, you are a wave that continually collapses and reforms. Your identity becomes a series of discrete, collapsed states, each momentary snapshot linked by the evolving wave function rather than by an unbroken classical trajectory. If many worlds holds true, your identity is not even unique. Countless versions of you diverge with each quantum decision, each equally real. Who then are you? Are you the all-encompassing wave function, the fleeting collapsed state, one branch among many, or the very process of collapse itself? Perhaps you are all of these at once. And the question, who am I, has no single answer in a quantum universe. One beautiful consequence of quantum mechanics is the freedom it introduces. Classical physics suggests a deterministic universe where the future is fixed by the past. Free will appears to be an illusion. Quantum mechanics, however, injects genuine randomness. When a wave function collapses, the outcome is probabilistic, not predetermined. No amount of information about the past can guarantee a specific future result. This opens a space where the future is not strictly determined, where chance and spontaneity can arise. Randomness alone does not equal free will, but it does create room for novelty and genuine uncertainty. You are not a clockwork automaton moving along a pre-written script. You are a quantum process, unfolding with outcomes that remain undetermined until they happen. This uncertainty offers a subtle form of freedom, a chance for the universe to surprise itself. Imagine the universe as a grand quantum field, a vast superposition of all possible states. Within this field, patterns emerge, localized excitations that we call particles, atoms, and eventually minds. These patterns entangle, interact, and occasionally collapse, giving rise to the appearance of a definite world. Consciousness arises within these patterns, still mysterious and not fully understood, yet it seems to play a role in selecting the stories we live. In this view, the universe is dreaming itself into existence. The quantum field is the dream, a sea of possibilities, while consciousness is the dreamer, collapsing possibilities into the narrative of reality. You are both a moment of collapse and a thread in the dream, briefly definite before dissolving back into the sea of potential. As you drift towards sleep, let this vision accompany you. In wakefulness, your consciousness keeps the collapse rapid and frequent, forging a solid sense of self. As awareness dims, the collapse slows, the wave spreads, and you drift closer to the underlying quantum field itself. In that gentle state, you become more like a pure superposition, less localized, more expansive. When you awaken, the collapse sharpens again, and you reform into the definite pattern you call yourself, ready to participate once more in the universe's grand quantum dance. You are wave and particle, potential and actual, one and many. You are the universe observing itself, collapsing itself, creating itself moment by moment. That is the nature of reality. Rest now in the knowing that you belong to something vast, strange, and beautiful, a quantum field waving through space, dreaming the cosmos into being. You have walked from the double-slit experiment to the mysteries of decoherence, from the wave-particle duality of light to the intricate tapestry of quantum fields. You have glimpsed how every atom, every thought, every breath is a dance of wave and collapse. May this awareness fill you with wonder, humility, and a quiet confidence that you are an active participant in a living, breathing universe. As you close your eyes, feel the wave within you, acknowledge the possibilities it holds, and trust that each moment of observation shapes the world in a meaningful way. Sleep now, knowing that the quantum field continues its silent song, and you are an essential note in its endless melody. Let that harmony guide you into rest, and awaken refreshed, ready to engage once again with the wondrous quantum fabric of existence.